Good morning, everybody. We've just initiated the workshop organized by Nanoelec in the framework of Date 20. It's probably one of the only events that will finally be organized this week, since the conference has been delayed and will be organized digitally. So thank you all for participating, and especially to the speakers that have accepted to commit to this new experience for us, because it's the first time that we organize such a webinar. And thank you for the organizers as well in the team, especially François Legrand, who has set up most of the work, and Marine, who is from Act and Match, who has helped us with the platform for this event. So I will start by a very quick overlook of Nanoelec to give you a brief overview of who we are, what we do, and then we'll have the main presentations of and the sessions going on. So in a few words, maybe to start with, my name is Hugues Metra. I am the director of Nanoelec since September 1st last year, so I'm still a little bit new in the system, but we've been running now with a new team for the past few months, and I will share with you some key points about Nanoelec. First of all, Nanoelec is a consortium headed by Leti that has been set up about 8 years ago now, and which is focused on semiconductor technologies and their applications. It's a consortium of about 22 members, a total annual budget of around 60 million euros, with funding from the French government as part of the French recovery plan that was launched in 2012 and 13. And through activities in the field of dissemination, we've been able to also partner with more than 230 companies, among which more than 180 SMEs, which is a very important part of our work, is to make sure that the technologies disseminate in the industry. And so, as you can see, we have a series of partners in the field of research and education: CNRS, Grenoble École of Management, Grenoble ENP, which is the Schools of Engineering, University of Grenoble-Alpes, and INRIA. CEA, the ILL, and the SRF are providing technology platforms that I will share some overview about them in a few minutes. We have key actors providing components, which is the core of our activities. So ST Microelectronics, of course, will have a presentation in a few minutes about the engagement of ST in Nanoelec. Almae, who is providing some 3-5 activities, Prophecy, Alidia, Soitec. We have equipment manufacturers. We have EDA tool software company, Mentor Graphics, which is part now of Siemens Group, who will provide 2 presentations this morning. We have network activities through Minalogic, the cluster in Grenoble, and through Jessica, with an association providing advices to companies when they want to enter the electronic fields. And then we have some end-user companies. The Nanoelec IRT is part of a larger network of French institutes of technology, which are involved in 2 main areas: technology research for industry on one side, and energy transition institutes. It's a network that has been developed over the past 8 years in parallel to what Nanoelec has been doing. The aim of all these institutes is that one of very specific part of our activities is that we do collaborative research. The idea is to bring together people along the value-added chain to work together on developing new technologies and bringing them to the market. And this is done with the support of the French government as part of the French recovery plan that I was mentioning a few minutes ago. As far as Nanoelec is concerned, we have 3 main technology programs developing new components. 3D integration, so we will have a session specifically on this. Silicon photonics, we will have another session on this topic. We have gallium nitride power activities, which is that has been launched about 2 or 3 years ago. We didn't plan any presentation on this topic today because the technology are newer, and we are not yet bridging the gap to demonstrators using EDA tools and the focus of IC design. So it's a little bit early. It will be for another time. And we have another program called PULSE, which is focusing today on cybersecurity, and this topic of cybersecurity will be the third session of the program today. And in parallel to technological development, Nanoelec has always been investing activities in the field of education and training to develop new training programs to adapt to the trends in nanoelectronics and to find new competencies and help develop new competencies for the industry. And the last one is the dissemination program with a program called EasyTech, which is developing and transferring technologies to SMEs in the region, but also at the French level. The model, of course, is based on technology platforms. That means that we use platforms provided by our partners, especially clean rooms. Of course, the ones from Leti, but also from partners such as ST, because some of our activities are developed and processed in the partners. We have technical platform to do demonstration in application environments, especially in the PULSE program. And today, as I mentioned, this program has been focusing on IoT and cybersecurity. So we have some platforms to demonstrate applications in the field of smart housing, silver economy, industrial environment, and so on. We have the large-scale instruments provided by the European scientific actors, ILL with the neutron source, and ESRF with the synchrotron, that provide tools to do characterization of semiconductors. And finally, we have the education and training platforms provided by Grenoble École of Management for the management school for the business training, and Grenoble ENP for engineering and technical know-how. If we come back to the topic today, the idea is to use the conference date to show how new tools like architecture and system design, data processing, IC design, and EDA tools are specific know-how and expertise that help designers and developers bridge the gap between technology development, which was initially our focus at Nanoelec. So either in 3D stacking techniques, silicon photonics platforms. If we speak of cybersecurity, we can mention some new ideas around specific function at the technology level, and the gallium nitride. And if we want to bridge the gap to the main application fields that we are targeting at Nanoelec, energy conversion systems, image sensors and displays, and secure devices and systems, the know-how that will be presented during the session today around IC design, EDA tools, and all the activities around are key to be successful in helping our partners go faster to the market. And so I will finalize my presentation with a brief overview of the objectives of the workshop today. The first one is to illustrate the value of multi-partner programs, which is, as I mentioned, the essence of Nanoelec, to demonstrate the importance of EDA tools and IC design expertise to help, as I just mentioned, bridge the gap between emerging technologies and applications, to highlight some of the results that we've collectively achieved over the past few years, and finally, to demonstrate how some of our members plan to use the consortium to address future opportunities. And so we'll now cover the agenda with a keynote speech from ST that I will introduce in a minute. And then we'll move on to the 3 sessions: 3D integration, silicon photonics, and cybersecurity. So I will step aside and leave the floor to Dominique Thomas. Maybe I can stay here for a minute. Dominique Thomas is in charge of institutional affairs for the R&D activities of ST in France. He has been in the field for a very long time with technical actions in SGS Thomson and then ST Microelectronics, but he has also been instrumental over the past 15 years to set up new initiatives that are funded by the French government, whether it's the Centre Commun de Microélectronique or the setup of the competitive cluster Minalogic a few years ago. And he was also very much involved in the emergence of Nanoelec over the past few years. So he will now give an overview of the actions of ST and the intents of ST in Nanoelec. Thank you very much. I didn't mention that we are providing an interface for a chat so that you can ask questions during the talks, and we will address them at the end of each talk to make sure that we try to answer most of the questions that arise during the presentations. So there is one.
Are the slides going to be shared after the workshop?
So yes, the workshop is recorded, and it will be available also as a virtual workshop, and the slide will be available.
Okay. Good morning, everyone. So it's my pleasure to introduce this workshop. Yes, okay. To introduce this workshop, and in the name of ST Microelectronics, which is one of the main industrial partners of IRT Nanoelec since its inception. So who is changing the slides? I am, okay. Sorry. I am. Yes, okay, thanks very much. So anyway, first, the ID card of ST. ST is among the largest semiconductor companies in the world, with more than 100,000 customers, and we have revenues last year of close to 10 billion at 9.56. We're listed in several stock exchanges, as you know, and also quite importantly, we are a signatory of the United Nations Global Compact engagement and member of the Responsible Business Alliance. We are 46,000 employees, 46, sorry, and with close to 88,000 in R&D, with 16% of our revenue invested in R&D every year. We also have 11 manufacturing sites worldwide, and notably in Europe, we have front-end manufacturing sites in Italy, in Milan, in Catania, and in France, in Tours, in Aix-en-Provence, and in the Grenoble area. Okay, yes, so I can change the slides. Our company, of course, produces chips essentially, and which address 4 end markets: automotive, or let's say maybe more generally mobility, is one of our big end markets. Industrial, that is chips which go into all kinds of devices of everyday's life, and also on the shop floor, on the factory floor. Sorry. We have also personal electronics. Of course, you see many handheld devices, and a number of applications in communications, equipment, computers, and peripherals in the networks. The 5G, we are very present in 5G, and all kind of network and personal computing equipment. quite important for ST, and sorry for this, the slides should have been changed a few days ago. We issued our new report, the 2020 sustainability report, but the address is still the same on the top right corner of the slide. You can find it on our website. It's quite important for us. It's been important for I mean, since the start of the company, to do as much as we can to preserve the environment, and also the well-being of our employees. Maybe one figure that is here is also we have close to 550. Last year, I think it was 560 patents application every year. And we have a very precise and concrete goals related to the decrease of our resource per unit production. Okay, so now coming back to IRT Nanoelec, I will drive you through a few of the application and interest of ST related to IRT Nanoelec works. And first, I will talk to you about the transition that has occurred in the company over the past 5 years. So IRT Nanoelec started in 2012. 8 years ago, we've been there from the beginning, and our interest into IRT Nanoelec works was a bit different at the beginning than later on. We notably have a range of business that we call imaging. That used to be the beginning of IRT Nanoelec, quite successful and engaged into camera modules for smartphones that we call now. We can call now commodity camera modules. And in the mid of the last decade, we have experienced a strong decrease in this market for us, because it became a commodity market that we could not address anymore. And we have changed, let's say, our positioning. First with time-of-flight solutions, time-of-flight meaning distance measurement equipment, still based on photon sensing, of course, and then on specialized image sensors, that is still cameras, but cameras which don't produce images that the user can see, which produce images that are used by automated processing in order to do some functions. And we have experienced good success in this market since 4 or 5 years ago, in those two markets, let's say. And the sense of this message is that the IRT Nanoelec was able to, let's say, support this change, this large change. And okay, I will tell you a few more words about it. Okay, sorry. Okay, so what? Sorry for my French, but I just reused a slide that was written in French, and I will translate what's on it. The four of the applications that are allowed by those new sensors that we still call internally imaging are, from the top left, facial recognition, then automotive safety, for instance, in-cabin automotive safety, and then bottom left, distance measurement, which can have a lot of applications related to, for instance, user detection, environment detection, robotics, etc. And then bottom right, spectral analysis, which you can find today in devices that we call ambient light sensing, the devices which allow your phone camera to output, let's say, a good image with right colors, but will be soon used to other applications, detection of maybe chemicals, whatever. All those applications require technologies that have been developed within the IRT Nanoelec, and the IRT Nanoelec, which was focused for technology-wise on 3D integration, that is the integration of silicon layers on top of each other, have been quite agile in helping us adapt those technologies which are initially developed for computing applications mainly. Let's say the connection of the memory to the processor in what we used to call application processors of the smartphones, have been applied to those new imaging applications. Okay, another example of the shift of the technologies that we've been involved to in IRT Nanoelec is the silicon photonics. We have been involved in the silicon photonics IRT Nanoelec program since the beginning. At first for optical communications. Now the focus of our company is more into sensing overall. And I give the example of LiDAR. LiDAR is also a distance measurement device, a bit more complicated than simple time-of-flight measurements that we have developed for the smartphone market. But still, it's a time-of-flight measurement, longer distance. And one of the difficulties of LiDARs for automotive or for other mobility devices is to integrate in a small volume and with a small energy consumption the beam steering, that is the scanning of the environment, the scanning of the optical field, if you wish. And today, existing solutions use mechanical devices. We've been working with IRT Nanoelec on using silicon photonics, that is the integration of the light processing onto the silicon surface for beam steering applications with convincing demonstrations very recently. So this is still upstream, but it shows also the capability of this program to address different applications than those that were intended initially. Yes. So next steps for us for those applications in imaging and other applications is to integrate more developments. As I mentioned, the new major developments for imaging involve stacking elements. Why stacking elements? Silicon chips. That is, you want to optimize the detection of the light and the signal analysis very close to the sensor. So basically, the best way to do it in order to leave more space on the upper surface, if you want, for light detection, is to integrate the two silicon layers or more. That is the silicon layer that will be devoted to light detection with the maximum surface load for collecting the photons, and a second layer devoted to close to the sensor signal analysis in order to decrease, let's say, the need of data transmission over high-speed data transmission over interface. And so we introduce processing at sensor level. It's very important. So it's very important to associate for these equipment makers and also software or design. And also to strongly couple the technology and the applications. We cannot develop a technology out of thin air and hope that the market will adopt it immediately. We have to have a number of feedback loops between the technology developments and the applications. So also, as you know, I've mentioned multi-spectral detection, and it's quite important also to study the way applications can be addressed with different spectral ranges. And so this is why also it is important to enlarge the ecosystem and to more imaging applications. And it happens that the Grenoble area, I need to speed up. The Grenoble area is quite rich in that respect. For instance, ultra low power, also infrared. Yeah, 5 minutes. Okay. So we the next steps in IRT Nanoelec will be to close the loop, to tighten the loop between technology and applications, and also involving education and training, because our field is changing fast. And it's very important that IRT Nanoelec involves also the education part. And I will just mention another area which is linked somewhat to the new mobility, which is the application of power semiconductors. And IRT Nanoelec has launched a program 2-3 years ago about gallium nitride. Gallium nitride and silicon carbide are extremely important wide bandgap semiconductors, which will allow, to put it into a nutshell, because I'm too long, to put it into a nutshell, to decrease significantly the cost of ownership of a fleet of vehicles, electrical vehicles, EVs, and put it well below the cost of ownership of thermal engine vehicles. So it's really a major challenge, and a major also issue. Put it together, the two technological direction. Of course, EV, remote control, autonomous vehicles will be the future. The imaging applications contribute to this in terms of sensors, and the power technologies contribute to this in terms of putting the electrical vehicles at the price of ownership level well below the thermal vehicles. And we have been invested in this field for a while. And the most efficient right now power technology wide bandgap is gallium nitride, and our tour in France factory and R&D center is betting a lot on this, together with IRT Nanoelec, which has developed key technologies and will continue. And in this field also we have other applications like industrial with other partners like Schneider Electric, which are involved into this, and it's quite important for us to have a wide range of let's say application companies involved also. I will go very fast now onto Pulse. The Pulse program, it's key to have this application, as I mentioned already. On top of what I've mentioned already, the Pulse program has allowed us to put to work our new solutions on security, which will be developed by my colleague Nicolas a bit later. And also next, the AI solutions will be key, and so it's very important to have this program as well. And we are also involved in, I mentioned training. It's essential. Our technologies, our applications are evolving at a very, very fast pace, and we need to develop the training needed for this. And characterization has been mentioned briefly. It will not be addressed into this webinar, but this is also important for the materials, etc. Key takeaway points, 1 minute. So for us in our R&D, a global R&D scheme, IRT and Nanoelec is used where a consortium R&D is most appropriate. That is sharing the risk at the early stage when the target applications are still in development, with equipment makers, with software makers, also other technologies together, and where the whole value chain is needed to get feedback. And as I mentioned, I think IRT has proven flexible enough to go from data-centric to sensor-centric for photonics. Also the same for 3D integration, and in Pulse with security applications, which was a bit different from the initial focus, and introducing power technologies as well. So we have new challenge. We want to tighten the link even more between technology and applications, while maintaining excellent and upstream technology R&D. This is always the challenge. And we want to integrate better the new technologies into the system vision. We associating the necessary activities to get more visibility. So thank you very much for your attention. There might be questions.
Thank you very much,
Yes.
Dominique. So we had a question during
the first question
which was about the distance measurement capability functions in the mobile phone based on the sensor that you mentioned, to use them for gesture recognition in smartphones, tablet, and PCs.
To be very fast, yes, it can. So yes, it can, and of course, gesture recognition is quite wide. So it's been used already, and maybe a multi-sensor can do a better work. There are many sensors which can be used for gesture recognition, but yes, distance measurement functions, especially when you have, let's say, a full frame or a few points, not just one point. Of measurement can be used generally, yes, but it's more complicated than that. But yes.
Thank you very much. So Dominique, we will be able now to close this first introductory part to the workshop, and we'll start with the first session on 3D integration technologies. The first, so you're still attending the Nanoelec workshop on bridging the gap between semiconductor technologies and architecture that has been initiated as a side event to date 20. Pascal is scientific director of the IC design, architecture, and embedded software teams of CA in Grenoble. He has been for a very long time involved in Nanoelec, leading all the effort on IC design for 3D stacking architectures and design. And he will present today the results of a project that has been running for more than 3 or 4 years now, dealing with a project on using 3D technologies for high performance computing. So Pascal Vivet, the floor is yours.
Okay, thank you, Hugh, for your introduction. So it's really my pleasure to be here. First time for me to do that kind of thing after many conferences. So I will present you this morning measure results that we have been achieving through IRT program that has been initiating many years ago, even more than 3 years ago. I will not recap all the story, but I will present some more detailed results about all the chips that has been presented 3 weeks ago in IACC conference in San Francisco with a measure paper. Oops. Okay, so in the context of high performance computing and big data application and all that project has been started in that domain, we continuously want to integrate more cores, more accelerators, more memory. It appears that similar constraints are also appearing for embedded HPC, which is automotive and avionics. So it is not only concerned for big computing farm. And in these domains, we need very generic functions and highly optimized in terms of energy efficiency. That can be either generic as CPU, GPUs, memories, but also highly specialized like machine learning and AI accelerators to answer the greedy computing demand of all these big data applications. In a sustainable world and economy, we need to find, as circuit designer, a solution in order to integrate all these functions and to provide easier system differentiation and a fast way to go to the market for that. It is not viable to do that in a single die solution using advanced CMOS technologies due to the cost and yield issues. And this innovation and this differentiation is not possible through a single die solution. And for that, I strongly believe that chiplet partitioning is the right way to go. For chiplet partitioning, system designers must offer modular, cost-effective solutions, energy efficiency of the system infrastructure, and more on-chip memory bandwidth per core. Actually, chiplet partitioning is not new, and it has been introduced many years ago, and we have been very active through the IRT Nanoelec program to introduce all these concepts and technologies. And the motivations of chiplet partitioning are well understood now by all the partners worldwide. First of all, it is driven by cost, because thanks to non-good die sorting, it's possible to yield large systems in advanced CMOS technologies. Second thing, it's driven by modularity, and chiplet partitioning allows a the very right way to do modular systems in terms of both functions and functionality and ecosystem. While heterogeneous integrations allows to pick the right technology. Oops. While heterogeneous integration allows to pick the right oops. Oh, sure. 2 or 3 seconds. Here we are. While heterogeneous integration allows to pick the right technology for the right functions, such as advanced CMOS technologies for computing, DRAM technology for memory, or OXRAM technologies for AI acceleration, for instance. All these chiplets will be integrated using advanced 3D technologies, which can be done using TSVs, microbumps, or even more advanced technologies. There are various chiplet challenges associated to all that, of course. The first one is the ecosystem maturity that will move progressively from IP reuse to chiplet reuse. While in terms of system-level design, this simple Lego cartoon with this nice picture here is not as simple as that, and it needs deep thought in terms of both technology and architecture partitioning. While various challenges are raised regarding circuit design, for instance, on chiplet interfaces, testability, 3D CAD flows, and so on. But now, if we are looking to the state of the art, there are actually existing 3 main kinds of technologies for chiplet partitioning. The first one is organic substrates, which is low cost and providing higher pitch, and it has been adopted, for instance, by AMD in order to do chiplet-based partitioning, presented 2 years ago, and with some very recent and interesting results presented 2 weeks ago in a ISCC conference as well. The second one is passive interposer, also called 2.5D integration, which is more costly, using more aggressive pitch, which is provided by foundry partners such as TSMC and their CoWoS technology, and which is currently used for FPGA or HBM memory integration. The last one, silicon bridges, is a trade-off between both, which has been adopted by Intel with their EMI bridge, which is a small piece of silicon bridging 2 different chiplets within the organic substrate. So all these technologies are mature on the market and are currently used in various products massively, but there are still some limitations. The first one, as circuit designer and architect, that we see is that the chiplet communication is limited to side-by-side communication. It is not scalable. We cannot scale to a large number of chiplets by using those technologies. It is not possible. The second one is how to integrate heterogeneous chiplets and differentiating functions through this modular assembly. And the last one is how to integrate less scalable functions such as IOS functions, analogs, power management to bridge between all these different options. And for that, we're going to introduce active interposer. So the principle is as below. So the idea is supposing that you have massive number of chiplets which are composed of cluster of cores, whatever they are. They could be heterogeneous as well. We're going to 3D stack them face-to-face onto an active interposer, which is a large structure containing CMOS circuits. In order to bridge all these interconnects, all these chiplets together, we're going to integrate scalable and distributed network on chips, allowing any chiplet to chiplet traffic. We're going to integrate power management close to the cores below each chiplet to power supply them. We'll finally integrate SOC infrastructure such as analogs, files, and design for testability, while finally some free space could be used to preserve and to bring additional features for heterogeneous functions. Mature CMOS technology must be used for such active interposer to preserve the logic density and to preserve the system cost. So after this introduction on chiplet partitioning, I'm going to present into more details this active interposer circuit and its building blocks. So we have designed a complete circuit called Intact, which is an active interposer composed of 6 chiplets, 3D stacked on it. Each chiplet is composed of 4 clusters of 4 cores, so this is 16 cores per chip, with a distributed hierarchy of caches with level 1, level 2, and level 3 cache style. The overall architecture provides a scalable cache currency memory hierarchy. We have 6 of them, and they are 3D stacked face-to-face onto the active interposer, which is integrating distributed flexible interconnects to make the connection between all these objects, integrated switch cap voltage regulator, 1 per chiplet to provide power management for each chip, finally memory I/O controller and system I/Os for chip to the system communication. The final image of the system is the following. And we can see the 6 chiplets in FD-SOI 28 nanometer technology, 3D stacked onto the active interposer and 65 nanometer technology. And in a nutshell, we are integrating 96 cores. We can notice that we have 2 different technology nodes difference between the chiplets and the bottom die, which is providing enough performances in terms of analog partitioning and IOs in the bottom die compared to the top die. Let's now present in more detail the chiplet main features. So each chip, it contains small 30-bit scalar cores. The memory is physically distributed throughout the IRT with level 2 caches and virtual memory support. And we have also adaptive and fault-tolerant L3 caches. And we have introduced and previously published new and innovative protocol providing cache currency through linked list directory. I will not enter into the details of all that. What we can see in terms of system-level interconnect, we have all these styles of computing and caches which are interconnected through 2D mesh NOCs. And we have 3 of them. The blue one, which is interconnecting level 1 to level 2 caches. The green one, which is interconnecting level 2 to level 3 caches. While the last one, the red one, is interconnecting the level 3 caches to the external memory. And those 3 interconnects are extended through the interposer using what are 3D plugs, which are called 3D plugs. Excuse me. So if we now focus onto the system level interconnects, so these 3 interconnects which have been introduced previously in the chiplet are extended through the active interposer and they are integrated as distributed and very flexible interconnects within the active interposer. They integrate multiple network on chips, which are composed of routers and links, which are integrating pipelining, buffering, and retiming for clock domain crossing. And we are also integrating 3D plug communication IPs to make the communication vertically between the chip and the active interposer. And we have 2 versions of them, synchronous and asynchronous version, in order to study different performance trade-offs. In terms of chiplet-to-chiplet communication schemes, we have 2 different schemes, either passive links for chip-to-chip communication without any routing and buffering, and we have active links for long-reach communication between L2 and L3 and L3 to external memory, which is allowing any chiplet-to-chiplet scalable traffic. If we zoom in terms of layout, how all that is done, this is the layout of the chiplet, and we can see the different clusters of computing with level 1 caches, level 2 caches, level 3 caches. And in each corner of the chip, we can see 4 3D plugs, which are providing the physical interface and the logical interface to communicate with the active interposer, which is just below. If we zoom in, we can see a matrix of microbumps, which is technology provided by the IRT program, which has been fabricated in the Leti fab, with microbumps with a very aggressive pitch of 20 micrometers. Below this matrix of microbumps, we can see microbuffer standard cells and the glue logic of the interface. And this interface provides this logic and pipelining interface, microbumps, standard cells, and testability features as well. If we zoom in the microbuffer standard cells, which has been done jointly between ST and ourselves, we have bidirectional drivers, ESD protection for clean assembly, pull-up and level shifters so that we can bridge the power domain between the top chip and the bottom chip. Main results about the circuit. The 3D plug, we have the best throughput for the synchronous version with 1.2 GHz. For the interposer, we have similar throughput between the synchronous NOC and the asynchronous NOC, about 1 GHz. But we have the best latency for the asynchronous NOC. Supposing that we want to communicate between that chip and that chip, we're able to achieve a propagation speed of less than 1 nanosecond per millimeter, which is 3 to 5 times better than the state of the art for synchronous NOC version. And we are very pleased for that. And this latency reduction is very important for cache currency traffic, but this comes at the cost of some energy. So with all these numbers, we see that we need a combination of different interconnect types to achieve different performance trade-offs. Let's now go to the switch cap voltage regulators. So as I presented below, we have distributed power supply units providing voltage and frequency scaling below each chiplets that are providing reduced IR drop effects. It is fully integrated. There is no external passive components, and we are using SiC oxide transistors using this 65 nanometer technology. We have only on-chip capacitance composed of MOS and MOM and MIM with a large capacitance density. And about 50% of the chiplet area is dedicated to this switch cap voltage regulator, which is integrated into the interposer. Regarding design for testability, we have, of course, some challenges in terms of testability. We need to test the dies for non-good die sorting. We need to test also the active interposer on the final package. And we have also some issues about test access because we need to test probes on some very small objects. So we are probing on some additional 2D paths. A flexible 3D DFT architecture has been proposed using combination of parallel scan chains and IJ-tag interface. I will not enter into all the details, but all that has been done and implementing using mentor tools called présente, which has been used for DFT insertion and automatic test pattern generation, and it has been published the previous years as well. We would like also to present some more details about the 3D design flow, which has been developed jointly into the program. So the main achievements, so we have done a close cooperation and optimization between the 3D CAD tools and the 3D circuit design, and covering wide aspects of the system of the circuit design aspects. Architecture, physical implementation, and 3D sign-off. In terms of architecture, we have been using expedition tools for system partitioning and packaging co-design, thermal profiling at system level using an advanced tool called Sahara for early thermal analysis, DFT using présente tools, and also sign-off with scalable tools for DRC, LVS verification, thermal sign-off, parasitics, and electromigration as well. We have also some early results onto thermal, but I will not present that into more details. I would like to spend more time onto the conclusion. So circuit results. Here are the cross-section of the design. So chiplets are implemented in FD-SOI 28 nanometer technology from ST, fabricated in ST Kroll Fab. Active interposer in 65 nanometer technology with MIM option, fabricated by ST as well. 3D technology has been performed by IT partners, so ST and Leti. And we can see the cross-section of the device with the chiplet, microbumps, pitch of 20 micrometer technology, active interposer in 65 with TSVs, allowing the cross to go from the front face to the bottom face and the package substrate. We can see here the floor plan and layout of the two chips, the chiplet and the active interposer on the final package. More cross-section of the device, which has been presented at the ECTC 2019 conference last May, which has received the Best Paper Award, and we are very proud of that, and with some very nice pictures and more electrical results. And we can see zoom of the two structures of the chiplet, the active interposer again on the copper pillars, and with clean assembly of the interposer to the package and clear alignment, which has been achieved. Circuit performances now. So circuit is able to achieve wide voltage range from 0.5 volts all the way to 1.1 volt using back biasing in FD-SOI. We're achieving a peak performance of 220 gigahertz for all the 96 cores at 1.15 gigahertz. Best energy efficiency is achieved at low voltage with an energy efficiency of 10 gigahertz per watt. Power consumption breakdown, more interestingly, we can see that about 2/3 of the overall system is dedicated to the chiplet, with half in the cores and the second half in the level 2 and level 3 caches, while only 3% of the interposer of the power consumption is dedicated to the interposer logic for all the interconnects for chip-to-chip communication, while 70% of the power budget is dedicated to the interposer switch cap voltage regulator, which are the power loss within the voltage regulator in order to power supply the chiplets. If we now compare to state of the art, so we are the first one to introduce, compared to previous work from Intel, AMD, TSMC, or Intel again, active interposer, which are integrating some extra features within the logic. High yield is expected on that kind of object. Aggressive pitch has been achieved for the microbumps. Voltage regulators achieves a very high energy efficiency as 82% because we are integrating all the capacitance within the active interposer compared to previous work, which were limited in terms of dedicated area available in that. While in terms of interconnects, higher bandwidth density of 3 terabytes per second per millimeter square has been achieved, which is 2 times better than state of the art. And we are the first one to report so many number of chiplets integrated onto a single substrate, with so many number of cores, about 100 cores. So let's conclude the talk. So through the IRT program and a program of about 5 to 6 years, I would say, it has been quite a long and very tedious effort by all the design and technology team to achieve those results. We have been able to show this chiplet partitioning onto an active interposer, integrating both interconnects, power management, and IOs. 3 terabit per second per millimeter square bandwidth is achieved, and this is a very high number in terms of state of the art, and we are very proud of that. Low latency interconnect using asynchronous interconnect is possible for long distance communication, while power management fully integrated allows to power supply the chip. All these benefits and IPs allows to increase energy efficiency and the chip memory bandwidth per core. Second conclusion also is that we have been able to set up through the IoT program a mature 3D design flow and tools thanks to an active collaboration with Mentor Graphics. For the perspectives, chiplet ecosystem, there will be a progressive setup of the chiplet ecosystem. It is already appearing for high-performance computing on the United States side. IBM, AMD, Intel, everybody is working on that, but it will also appear very shortly, and we are working on that, on embedded HPC for automotive and AI acceleration. An active interposer can be an enabler for differentiation, integrating heterogeneous functions on chiplets. More perspectives. The first one is in terms of technology, aggressive hybrid bonding, fine pitch, chip-to-chip interconnect with 3 to 5 micrometer pitch is ongoing work to optimize chipletization. And the second one is photonic interposer for more chip-to-chip bandwidth and lower latency. So I really thank you for attending this talk and presentation. If you have any questions, I will be pleased to answer it.
Okay, so there is a question from David. Do you have any views, or can you share any views on the standardization of the chiplet signaling and protocols?
Okay, thanks, David. So this is really good question, and there are many initiatives worldwide on that. There is one standard group working on that through the OCP standardization industrial group, and the group is called ODSA, Open Design Standardization Hardware, something like that. I forgot. And we have not been participating yet, but we have discussions about that, and we know the people. And clearly, chiplet standardization will be a way to bridge all the chips together onto those substrates. And the second question is that as long as those standards are not existing, because many people will provide their own chiplet with their own protocol. So suppose that you have chiplet A with protocol A, and you want to integrate it with chiplet B of protocol B. The only solution to bridge them is to use active interposer to glue them together through active circuits within the active interposer.
Okay, thank you very much, Pascal. So I guess I suggest that we move to the next talk.
Many thanks.
This talk will be given. So the next talk will be given by Jean-Luc Jaffard from a French company called Prophecy. Jean-Luc has worked a very long time for ST Microelectronics, where he initiated and developed the activities on imaging. So it's a field that he has been involved in for a very long time. He left ST in 2014 to join a consulting company called Red Belt Conseil, and joined Prophecy, a French startup specializing on biomorphic sensors to detect events in image sensors. And he will share with us the activities of the company and how the company sees opportunities in the field of 3D stacking, which has been a main field of Nanoelec, as you mentioned. So as I mentioned before, Jean-Luc is intervening remotely, so we will give him the floor now.
Okay, I will start. Okay, good morning, everybody, and sorry for not being with you this morning. So it's a pleasure to present the activity of Prophecy and the interest of the company to join a consortium like the 3D Nanoelec. Okay, so first of all, just to introduce who is Prophecy. Prophecy is a French startup company created 5 years ago. which is exploiting a technology developed by some UPMC and Vision Institute in Paris, which try to mimic the behavior of the eye of the retina and the way the information are transferred from the eye to the brain. So the company is now around 100 people who are mainly based in Paris with a site in Grenoble and the sales and marketing site in US and Asia. So we are doing three types of things today. We develop a hardware and software component. We develop a solution with a complete camera, and we have a complete development system, including the camera and the processing. And the first component are now on the market with industrial product. So this technology is it's an imaging technology, but we call it is an imaging sensing technology. So that's been for many years the imaging industry has focused on improving the image quality. And we have seen the evolution over the last 15 years with the cell phone, which has pushed this industry and the technology to get a very good result. We are not really in this domain. We are domain of the sensing. So that means where the importance is the action is not the quality of the image. I'm not saying that this does not require efficient sensor and performance sensor, but the purpose is really to sense the image and not to display and print the image. So what is the base of the technology behind that is that we consider in an image or in a video, there are a lot of redundancy and a lot of inconsistency in the image. For example, here in the baseball, you can see on the top part of the image, there is basically oversampling. So that means we cannot see the detail, and the detail of the image will be limited by the optics and the resolution and the sensor. But on the other side, around the arm, where there is a very strong motion content, the image is, with a classical sensor is undersampled. So that's mean all of that thing that fine for a normal image, it's maybe acceptable, but for when we want to have a very fast motion detection, interpretation, and optimization is not the ideal thing. And this undersampling will create a motion blur that will create distortion of the image. When the oversampling part will create a redundant, useless data, okay, which are, let's say, for high resolution sampler may occupy a lot of bandwidth and so on. So what is an event sensor? What's the event sensor is moving from if you look on the left side, the standard camera, we frame the sensor and we sample this image on a fixed time with the classical sampling base. On event sensor, the samples, the pixel are samples only when the pixel detect a change. So that means in a scene where there is no change, no motion in the image, basically the sensor will not deliver any information. So the benefit of that is that we can, in case of the change in the image, we can generate a very fast response, and that's eliminate blur and this kind of thing. So a totally different concept where we have not something repetitive, we move from something which is asynchronous to asynchronous, and that's make possible to reduce drastically the amount of data and in the same time to have a very fast response. Okay, so the same thing, sorry, I think the PDF will not show the video here. Yes, it's the case, and sorry for that. But in fact, this type of sensor allow to transmit information in permanence. So that's mean if there is a change in the scene, the sensor will detect this change and will continue to send information. So that means you will not have a discontinuity in the generation of frames. So if I can make an illustration of that, if you have a camera in a car, this camera, a frame-based camera, we sample every X frames, so every X 10 times or X 100 times per second the image. And during this time, the car can move and something can happen. With an event sensor, we will monitor continuously the change of the image. So that means it will generate a lot of events, but only on the part which is changing. So that makes a very complex, different way of approaching the image. The benefit of the technology, we see four major action. Detection is that, as I mentioned, the detection can be extremely fast. The prediction is that we can detect only the part we change. So that means it's pretty easy to make interpretation of change. The robustness is that each pixel is independent, and therefore we can have high dynamic range, independent pixel to pixel, and efficiency is a limited amount of data transmitted from the sensor. Okay. I have a bit of problem with that. Okay. Fine. So where do we find this technology? We can find this technology in industrial automation, where fast motion detection is required. We can find that in IoT, where the opposite is low power, and automotive. I mentioned about that, which is the speed. Now, if we look what happened over the last, let's say, 20 years in the sensor. So on the CIS sensor, we move first from let's say the first concept in the late 90s, what we can do the sensing and the processing inside the chip. So basically, we have the sensor plus the image signal processing, and attached to that in the system, there was a processor somewhere. After that, we move to a step where we separate the image signal processing, which is the image reconstruction, from the sensor itself. And we had solution with basically three components: a sensor, a coprocessor for image restoration, and a processor for the main topic. And step by step, we move to something where we go back to a sensor plus the processing of the ISP, thanks to the first level of stacking with two wafers. And then we can start getting something processing close to the sensor. And the way we see in the future is that, in fact, we will continue this integration, but not having let's say the first level of processing, but having the compute close to the sensor. And that's where we'll continue this integration. So we see over the year that the initial idea of having all the processing close and inside the same sensor will happen now, I think, in second half of the 2020, with a full automotive sensing and processing system. Okay, so I will quick around that. That is the evolution of the 3D image sensor technology, with we move from the front side to the back side, first with the TSV connection and then to hybrid connection. We'll come back a little bit later on that. This is not new in terms of image sensor. The first 3D hybrid sensing sensor was introduced in 2013 with the TSV stacking, and move step by step with the hybrid stacking. Okay. Now, as I mentioned before, we have a lot of processing in our pixel, and I try to make a distinguo here between what I call the embedded processing imager and the in-pixel processing imager. The embedded processing imager is the sensing, but okay, it requires small pixel, advanced technology. It requires imager and CMOS compatibility to have some local processing, and it's very often driven by the small pixel size. The in-pixel processing imager is that it's again a CIS sensor, okay, but is also an SoC imager, and each pixel embarks a lot of components. So that means when you have a pixel with a lot of components per pixel, the shrinkability of this pixel size is questionable, and very often it's ended with a very large component size with very large optical format, and basically not a very cost-efficient solution. So how to address that? So the 3D process for imager address this problematic, and there are two. If I compare again the embedded processing imager with the in-pixel processing imager, the embedded processing imager, basically what we see, the CIS layer is mainly composed of the pixel array, and all the processing, either analog or digital, is put on the CMOS wafer, and we are generally speaking about, let's say, hundreds or thousands of contacts between the two wafers. On in-pixel processing, the situation is slightly different, because all the size of the CMOS process of the bottom wafer below the pixel array is used for the in-pixel processing. And the extra processing, either analog or digital, will occupy an extra place on the bottom wafer. So that's mean, just to bring one point, which is okay, that means there will have a question of optimization between the two wafers. And here we are speaking about hundreds K to millions of contacts between the two wafers depending of the resolution of the sensor. Okay, now as soon as we speak about those two wafers, and that I mentioned that potentially there is a space in the top wafer to do something else, that bring the question: what is the best choice? What can be done in the first wafer, in the top wafer, and what can be done with the bottom wafers? So that's immediately bring a question: is there is a room here to optimize not only the process, but to optimize the partitioning and therefore the cost of the solution. Okay. So now, coming back on the prophecy pixel. So I illustrated on the left a pixel that we have implemented in an FSI CIS 180 nanometer process. It's a 15 by 15 micron pixel, and we have a fill factor of 20%, and we have around the 50 component per pixel. So we can, just looking at the layout of this FSI pixel, the interest and the benefit of the stacking is immediate. We can see that if I just move all the component to the bottom wafer, I will reduce by 4 the pixel size and our fill factor close to 100%. So that means here we are doing really a lot of processing inside this pixel. Okay, so it's fine, but the partitioning between the two wafers is important for the processing, but is also a question mark for the pixel itself. So here I try to illustrate the first stage of our pixel, which is a diode with an amplifier and a few components. So there are different ways to split that, what we do in the top and what we do in the bottom wafers. And I put some red dot here to see, okay, we could put the connection between just on the top of the diode, we could put the connection on the output of the amplifier, and so on. And you see immediately that that's generate a lot of discussion around the optimization, because where the split will happen between the two wafers will have an impact on the best way to optimize each of the process for the top and bottom wafers. So here, I will go quick on this slide, but just to illustrate the benefit from a system point of view to have the right partitioning. I've looked at the ratio of the size of the pixel without, on FSI, that's mean without a stack, so what we can get with a stack with the minimum diode. And you can see that just playing with the ratio of integration, the way you reduce from the FSI to the stack, can have a big difference on the capacity you can plot inside the same optical format and the resolution that we can reach inside the same optical format. And it can be very significant. So if I take two examples, you have a diode of 2 micron with a fill factor of 16%. I can put in a half inch, you can put roughly 1 million pixel resolution. If I put a 4 micron diode, okay, with a fill factor for close to 100%, which is the case in case of stacking, basically with a 1 inch format, I will put roughly 7 megapixel resolution. So you see that the compromise between the integration between the two wafers is very important for the cost of the total solution, because it's not only the cost of the solution of the silicon, but it will be also the cost of the optics and mechanics and so on. Okay. So in the ideal world, I would say that when you are a designer, a sensor designer, that you want to use a stack pixel process, you should look at different things. Basically, the size of the diode and its performance, the fill factor, the ratio between analog and digital, okay, the sensor device, same thing, the CIS wafer and the CMOS wafer, which technology node are the best. Depending on the application, you may have interest to use a much more advanced CMOS node, the bottom wafer, than the other. Okay. And another thing which is important is what is the CIS process and the CMOS process compatibility. In the case of a stack, basically we can separate the performances and the constraint of the detections part with CIS and the CMOS can be completely separated. Obviously, from an application point of view, stack and BSI has an impact of cost because we are putting two wafers together. So that means it requires even more constraint on the quality of the design, because at the end, the total cost of the chip will be the combination of the sum of the cost of the two wafers multiplied by the yield of each wafers, including the bonding of the two wafers. So a new challenge for the designer people to be sure that they achieve the right technology. I think one thing is okay. So now, if we look at for the future, we think that more and more the sensing will become something standard, I would say, but the differentiation and the added value will come from the computing. And we are convinced at Prophecy that the evolution of at least the sensing sensor that we are developing will embark more and more processing locally. Because one very simple concept on that is, if you have a sensor which is extremely low power, why are you going to burn a lot of power just to transfer the information? And why on a sensor which is totally asynchronous, is there interest to do synchronous processing? Is maybe a benefit to do asynchronous processing and to have, in the same time, the power consumption and the size and the amount of data transmitted are optimized. And is why we think, and we are convinced that the future, let's say, of this of the technology for us will go to multi-stack technology. There was a first implementation on triple stack that was mainly used for slow motion, and there was done with one CIS wafer, one DRAM, and one digital wafer. On our application, we have a slightly different view. We think that the first level will still be an optical wafer and optical performances. The second one will be at least a CMOS, but the third one may be also a CMOS with a different technology node, which something will be very low power, very, very high density to make all the computing local. So in the conclusion of my talk, as you see, that's seen from the user point of view and for the application point of view, there are multiple ways to define an intelligent sensor and the way to use the 3D process variant. The benefit we see is that with such approach, the CIS, that means the sensing and the CMOS process wafers, can be totally optimized independently. So that means that we can have evolution of one of the two wafers depending on the application and the product complexity. Okay. Obviously, the challenge of the design will be that the design will have to cope with the combined process spread of the two wafers. Okay. The 3D BSI PIX process build for company for solution when we have in-pixel processing, obviously, is the route to improve the fill factor and you reduce the pixel size and to make the technology more scalable. Okay. The challenge of how you fit the processing between the two wafers is really something that the designer have to think about at the very early stage of the design. And obviously, even if today the offer are limited, what we think in the future is that they will have more and more different type of offers, either on the sensing part or on the CMOS part, that can be used to optimize the solution. So thank you for your attention. So if you have any question.
Thank you very much, Jean-Luc. We had one question from David that we can take.
Yes.
If the interface, the pixel processor and the digital compute is not a frame buffer, what is it?
It can be, okay, it can be, well, when we have an event sensor, okay, event-based sensor generate. Okay, so I will answer. I hope you switch off. Okay, between the pixel processing and the digital processing, it can be, we generate the stream of the event, and this event has to be processed, okay, as a stream. I'm not saying that in the compute there is no frame buffer, there is not high amount of memory, but is to compute the event is not to compute the image. It's not exactly the same thing.
Okay, thank you very much, Jean-Luc. So we can move on to the.
Question.
Oh, there is another question from Jean-Marc Talbot. what are the main markets of Prophecy? Are there already systems embedding Prophecy chips in industrial applications or industries?
The first market that will be addressed by Prophecy is the industrial automation market. And there are camera available. The first industrial camera available on the market is coming from a German company called Imago. You can buy any camera you want from with this our technology inside.
Okay, thank you very much, Jean-Luc.
Thank you.
So we are moving to the last presentation of this first session on 3D technologies. It will be given by Christophe Vinard from Mentor Graphics, also remotely. Christophe graduated from an engineering degree of a school in Lyon and a master's degree from INSA Lyon about 20 years ago. He has been working for many EDA tools vendors and companies, holding positions from application engineers to program management and business development. He is now working with Mentor and will share how some of the tools of the Mentor graphics suites have been used and developed and optimized for 3D stacking IC chips and architecture exploration.
Hello. Do you hear me? Hello, hello.
Yes, we can hear you.
Good. So good morning to everybody. Thanks for joining. I'm working for Mentor Graphics now for a little bit more than 15 years ago. I'm in charge of the digital platform implementation that I'm going to present you today. The speech is going to make the links between the current market trends that Mentor is trying to address versus the 3D integration and the collaboration that has taken place with the Leti and other partners for now many years. And the purpose of this talk is to show that Mentor is able to provide more and more tools to basically fulfill the requirements of such technology. So the agenda is going to be the following. I'm going to present you today what is the current 2D low power landscape of the Mentor digital implementation platform. Then I will give you our vision about 3Ds and basically how we are going to try to help the IRT Nanoelec smart imagers to basically move forward based on what Pascal Vivet already explained and basically what Jean-Luc Jaffard also has just explained us in terms of requirements, and give you a quick snapshot about what we have put in place, the roadmap for 2020 in the IRT Nanoelec 2025 for Smart Imager. So today, Mentor Graphics is basically able to propose a complete C to RTL to GDS implementation solutions. That was not the case 10 years ago. Step by step, we managed to put in place all the different bricks to be able to build this digital implementation flow. As you have understood, there's been already many collaborations between IRT and Mentor Graphics around Tessent, for example, for the design for test, around Calibre for everything which is extractions, and DRC LVS. What is important to understand is that with the new requirements of 3D integrations, a tool like Catapult, which is a high-level synthesis tool, which is basically providing a way to move from C to RTL, is becoming an important technology bricks, in the sense that now if you are thinking about 3D integration with 3 layers, you're going to have in the smart imager area, you're going to have always the first layer in terms of pixel layer. Second layer is going to be a processing layer that can be seen as a mixed layer. And generally what we are seeing is that the third layer is also going to be a processing layer, but more oriented towards AI and neural networks. And in this area, HLS is bringing high value. and this is going to be one of the topics that is going to be addressed during this IRT 2025 exploration. PowerPro is tightly linked to Catapult in the sense that this is a tool which is enabling to optimize the RTL to be even more low power. I'm going to give you more details on that. Oasis RTL is a physical RTL synthesis tool, which is embedding all the required physical notions to deliver a get level netlist, which is going to be physical aware. Présente is the entire platform, and today the market leader for test insertion and ATPG. NitroSoc is our place and route tool. NitroSoc is the next generation of a tool called Olympus SOC that has been previously used in some IRT Nanoelec work a couple of years back. Now this new generation is bringing more power and is going to be used to basically address the new needs for 3D integrations. And we have also a set of new tools. So Calibre Exact is known, Calibre DRC-LVS is known, but we have also a new tool called Blue Wave, which is a tool to do power integrity. So everything which is IR drop, either static or dynamic, and electromigrations, and also Optimus DS, which is a static timing analysis tools with, I would say, sign-off accuracy. So with this flow, basically Monto-Graphics is trying to address mainly two market trends. The first market trend is definitely higher level of abstractions with the high level synthesis, and bridging the physical tool like RTL synthesis and place and route to the HLS worlds, and also trying to address every ultra low power market, which are now not only in the IoT, but also in automotive, in neural networks, and also which is a problematic in 3D integration. So we believe that our visions are matching quite well with the 3D integration requirements. So PowerPro, just to give you a flavor of what the tool is able to do and what are the benefits of such a tool. First of all, the tool is able to work with any kind of RTL structures, and is also integrated into Catapults. So basically, is going to be able to automatically or manually, depending on how strong the designers are, to reduce the number of toggles and to remove unnecessary toggles while keeping the correct functionality of the chips. Okay. So if we look at some basic example, by having a sample RTLs, by using RTL Pro either standalone or inside Catapult, you are going to generate a new RTL, which is going to improve the way of putting in place, for example, clock gating, and which is going to address some unnecessary toggle in your get level structure. So this is very efficient. This is used in many IPs providers. This is used at ST, and this is part of our ultra low power solution. In terms of RTL to GDS, we believe today that we have every techniques, either in Oasis RTL or in our place and route flow, to be able to optimize the low power, both at the RTL level, at the gate level, in the leakage area, and in the dynamic area. So concerning RTL power analysis and optimization at RTL level, we have all the clock gating optimizations, which are available either in PowerPro or in Oasis RTL. We can handle, obviously, multi-VT power optimizations. And we have also an accurate power estimates based on physical layouts. We need to keep in mind that every tool which are starting at Oasis RTL, NitroSocs, and below are fully physical aware. Also, we have worked for many years with people doing extremely complex multi-voltage design, like, for example, ST Ericsson or MediaTek or Qualcomm. And we have today solutions for multi-VDD and multi-voltage architecture, which is, I would say, completely exhaustive. We are able to support any kind of multi-voltage setup. And you also need to keep in mind that the motor flow is the unique flow which is natively UPF based. When we started to develop our low power flow, it was back in 2006. It was the beginning of the standard UPF format, and we started from there, from scratch, which was not the case of other competitors. Obviously, our database is completely multi-corner, multi-mode, and the way we are using the low power optimizations is obviously tightly linked to our timer. So the power state tables and the multi-mode, multi-corner timers are obviously very tight together. And we have new techniques, other techniques of reducing dynamic powers, and these dynamic powers are taking place as soon as you enter into the place and route worlds. This is a lot of work that has been done with NVIDIA, and today we can work at every level of the gate level netlist, either on the clock tree synthesis aspect or on the data path at every level. So before placement, after placement, and after post-route optimization. So when I'm saying that we're able to handle complex multi-VDD designs, I mean that we're able, obviously, to handle any kind of voltage flavor in the designs. We're able to handle any kind of switchable power domains. We're able to integrate any kind of power switches strategy, either peripheral or distributed. We are also able to obviously handle all the required special cells for multi-voltage application like ISO, buffers, isolation cells, level shifters. We are also able to handle gas stations and always-on buffering to do feed-through buffering in terms of switchable power domains. So all these stuffs are available. This is something that we are using today in many designs, in many technologies. And this is something which probably are going to be used in the 3D integration as well. Very quickly, just to explain how we are also addressing low power optimization in place and routes. There is a lot of techniques in terms of automatic leakage classifications on the standard cells, leakage aware timing optimizations, and using obviously safe file or other activity files to control and drive the different optimization techniques which are taking place all along the flow, which is basically place in free place, clock, and routes. So this is basically our offering in terms of 2Ds. This is widely used. What we believe is that 3D integration is going to bring us to the next level of power optimizations. So there has been some brainstorming inside Montour R&D. I'm going to present you what is our positioning and how we are going to align with all the works which are going to take place in the IRT Nanoelec for Smart Imager. So first of all, without thinking about the way we are going to connect the pixel layers to the first CMOS layers, I'm going to mainly talk about the processing layer, so either layer 2 or layer 3. We take into considerations two techniques, the face-to-back and the face-to-face. So today, our opinion is that the face-to-face is much more difficult to put in place, basically because this is not going to use HD TSV, and the way of modeling the face-to-face via is quite difficult. This is not as simple as modeling face-to-backs TSV via. So we believe that this is going to have a large impact on our concept of layer promotions for timing optimization, and also nonlinear timing jumps impacts on sign of correlation. The second point is about partitioning. So the question is, how do we perform the associations of the different processing modules onto the different stack? So are we going to go for gate level or block level stacking? We believe this is design dependent. something is sure is that partition maps very well onto block level stacking. This is going to basically enable us to have a few connections between the tiers, and this is also going to be easier to basically fix some connection up fronts, which is not something that is mandatory, but this is going to help anyway the way we are going to assemble the tiers. And staggering logic block across tiers leave also too many connections. So this is we would like to avoid a fully staggered gate level stacking, which is going to induce too many connections. So basically, our analysis is that it's good to have an hybrid approach between gate partitioning and block level partitioning for face-to-back approach. And what we propose is to have basically segmentations of the designs, which is going to basically place groups of modules like clock, scan, or multi-voltage logics on separate tier from the data cells. These cells very often have a big impact on standard cell placements, and the connections are also limited compared to the data path connections. So we see an advantage of basically splitting those structures in the 3D partitioning. Also, we want to put the clock and the scan pins close to the interface because obviously this is going to reduce the variability and the distribution. There is more ideas obviously in terms of hybrid face-to-backs implementation. First of all, I'm currently talking about logic on logics, but we can have memory on logics, and obviously placing memory on the opposite tier from the logic cells is going to be to ease the implementation process. We can also place logic cells close to the associated memories, which is going to minimize the connection distance, improve the QR of this path, and also avoid fracture floor plans, which are often seen with designs which have a large number of memories. So this is going to be beneficial for design like network blocks and neural networks. So as a conclusion, other I would say benefits of the hybrid approach in terms of 3D compared to the 2D approach now, which basically is mainly being challenged by either congestions or density, is that by having this hybrid approach in face-to-backs, you are going to basically optimize the way standard cells are partitioned and placed. So you are going to decrease the wire length, you are going to decrease the density, and this is going to obviously help both power and area. And this is also going to help routing congestions by simplifying the routing networks and basically splitting the different hierarchical modules optimally versus the different usage of those modules. So we are believing that this is also going to help not only power, but the overall implementation approach. So today, our recommendations is we have a preference for face-to-backs between obviously the processing layers. I'm not talking about the pixel layers versus face-to-face. We believe that an hybrid approach by splitting clock, scan, multi-voltage, macros, and memories are included between different tiers is the best trade-off in terms of density and QR. And we see a clear benefits, obviously, of having a 3D approach in terms of powers compared to what we are able to do today in 2D. So just as a conclusions, we are currently working now with Leti and Sébastien Turiez, more specifically, towards implementing two-layer stack approach for processing in the IRT Nano for 2020. What we have decided to do is to have target heterogeneous integrations of C40 and C20. It's always easier to have two layers on the same technology, but this is already demonstrated and we want to move forward. So we are going to use C40 on the layer 2 and C28 on the layer 3 with the logic and memory. We are going to use HDTSV for phase 2 back 3D contacts as a VIA. So this is this is already validated, and this is basically a tuning of the technology files, both in terms of physical abstract and also RC extractions. And we are going to use Oasis RTL to do the synthesis and NitroSox to do the place and routes. And we believe that for by the mid 2020, we'll be able to have a first place and route floor plan with the power grids, with the partitionings on the two layers, and then we will move forwards placement, clock tree, and routing. That's it for me. Thank you for your time. If you have any questions, please go ahead.
Okay, thank you very much, Christophe. I think we didn't have any questions on the chat. Maybe one question from me. Based on some comments of the previous presentation from our colleague, did you notice a stronger interest in 3D EDA tools from the market as a whole? I mean, the semiconductor actors and the fabless companies doing designs.
So the answer is yes, and the answer is yes. 3D integration is something that basically has started a little bit more than 10 years ago. We see an acceleration, definitely, both in terms of EDA vendor and also in terms of, I would say, foundry themselves. Obviously, there is multiple new trends like machine learning, AI, neural network, which are taking place in the way we are implementing our software. But 3D, definitely, from my perspective, is starting to take off.
Okay, thank you very much, Christophe. So this is the end of the 3D session.
I just asked the question.
So another comment, sorry. So there is a question from Pascal. You mentioned parallel place and route between coarse grain layers. Sorry, how would you handle 3D interface allocation?
So this is this is a good question. So today, the way place and route tools are working are basically 2D, but there is you can actually extend this 2D capability by using specific properties in the system, like cover property, which are going to allow you to basically place cells over cells. So this is the way we are going to start the interface allocations. And then in terms of HDTSV handling, our aim is to basically try to fix them upfront, but this is going to be difficult. So we believe that by modeling those objects as macros and letting the router basically handle those special VIAs as regular VIA are going to help us to do these interface allocations. So if the question is also on the partitioning side, this is something that we can handle at RTL level. And this is going to be driven by the designer. We will not let the tool basically choose the layer allocation.
Okay, thank you very much, Christophe. So let's conclude with this question, the first session on 3D. We are still connected to the Nanoelec workshop on bridging the gap between technologies and architecture. We'll take a 5 minutes break because we are a little bit late to restart at 10:15, so we keep the initial schedule. It's very important when we are on a digital interface like ours. And the following presentation will deal with will open the session on photonics. Thank you very much. We are resuming the workshop after this longer break than that plan. So Quentin Villemar from Leti will continue the presentation on the silicon photonic platforms at Leti.
Thank you. Good morning, everyone. So I'm going to present the Silicon Photonics platform of CLAT. Okay, so this is the outline of my talk. So I will start by presenting the Silicon Photonics lab, and I will review the main applications of the lab. Then I will present briefly the fabrication platform and the device library, and I will spend time focusing on some building blocks which are very important for photonics. So very good results that we have on low propagation losses waveguides. A way to do 3D photonics to stack layers to have waveguide in silicon and in silicon nitride. I will present main active devices, modulators and photodiodes, and a way to integrate 3.5 material on silicon to make hybrid lasers. And I will finish by presenting what we do in the 300mm platform. Okay, so the Silicon Photonics lab of CLAT, we have 4 types of activities, which are first design, optical simulation, but also design kits. Then, of course, fabrication, so process integration and processing of the wafers in 200mm and 300mm platform of Leti. Then we can very advanced capabilities in terms of testing with automatic prober of 200 and 300mm. So for optical test, but also electrical up to 64 gigahertz. And finally, packaging of circuits to make module demonstrations. So now let's review the main applications of Silicon Photonics. So I will start with a historical application, which is high-speed interconnects or datacom. So it's historical in the sense that Silicon Photonics was first developed in our lab targeting this application. And it's now quite mature as some companies are already selling products based on Silicon Photonics for datacom. But still, it's very important applications for us, and we still work a lot on this type of circuits. And it's a good way to understand the main building blocks of this application because they are used in other applications too. So I will describe a little bit the different circuits that we have in datacom. So transmitter and receiver circuits. So in the transmitter circuits, for example, you have first a laser source, several lasers if you want several wavelengths. Then you need a modulator, electro-optical modulator to convert the electrical data to optical data. And then you want to combine the different wavelengths, which are different channels, using a multiplexer. So then the light is in a single waveguide, and you want to extract light from the chip to an optical fiber, and then you use a coupler, for example, a grating coupler. So then the light is traveling inside the data center in an optical fiber, and it's going into another circuit, which is called the receiver. So still you need a coupler, a grating coupler to get back into the chip, a demultiplexer this time, and a photodiode to detect the signal and to convert it back to electrical. Okay, so this is a very important applications, but we have some other applications that we target now. So the next one that is an emerging application, but we have many projects going on this application is LiDAR. So using photonic circuits to make optical phase array to scan an area, for example, in automotive applications. And it's a way to scan the area with light without any mechanical parts. So it's much more compact than a mechanical LiDAR, for example. And so we have many projects in progress concerning this application. Another emerging application is neuromorphic computing. So it's using photonics circuit to do calculations which are useful for artificial intelligence. So we are a little bit less advanced on these applications, so I go faster. But it's very interesting to make this type of circuits to have faster calculations. Another application which is emerging, but for which we are very active right now is quantum photonics. So quantum computing, but also quantum computations. So in both applications, computing and communication, the type of circuits and the building blocks are similar, and it's described on this circuit here. So as we deal with quantum, we are manipulating qubits, and qubits are photons, single photons or photons pair. And first you need to generate qubits. So to that, we need a resonator and generate a ring resonator. And we have to have a good generation of qubits, we use nonlinear effects. And to have something efficient, we need very low propagation losses in the waveguide. And we have the world record, actually, in terms of propagation losses in silicon nitride ring resonators with 3 dB per meter. And we were able to demonstrate frequency comp, as shown on this spectrum here. And each line represents entangled photons, symmetric with respect to the central line. So then when we have generated the qubits, we manipulate them inside the circuit, and more classical circuits made of interferometers. And at the end of the circuit, you need to detect a very few number of photons, so generally it's single photons. And for that, we need superconducting detectors, and we're working on developing superconducting detectors on silicon waveguides. Okay, so I reviewed the main application, so now I will give you some information about the fabrication platform. So this is a view of the fabrication platform. So it is a cross-section of the different layers that we use and how we integrate them together. And so this platform has been developed as part of the IRT program. So it's based on SOI wafers as a starting material. And then we have a lot of patterning steps for silicon, but also for doping layers. Then we can integrate silicon nitride layers. We can integrate the heater level for phase tuning, and the back end of line with 2 levels of metals. So it's more than 200 steps, fabrication steps, 24 lithographic levels, and a lot of different devices that we can make out of this fabrication platform, with some example on the right with SCM pictures. Okay, so now I will detail some results that we have on some building blocks that are useful for the silicon photonics platform. So the first one is very basic, but it's very important too. It's a silicon waveguide. So we had a very important work as part of IRT Nanoelec in collaboration with CNRS LTM lab in order to reduce the roughness of the silicon waveguides. And by reducing the roughness of the waveguides, we have dramatic reduction of propagation losses of this waveguide. And so we had very, very interesting results on a specific process, which is a smoothing annealing at high temperature and presence of H2. And the reduction in terms of propagation losses is shown on the right graph here. You see in orange without this process, propagation losses, and in blue when we apply this process, and the reduction is very, very large. And we have now the state of the art in terms of propagation losses. And so this process is now integrated in the platform, and it's offered for our partners. So it's a very important result for us. Another building block, I already spoke about that, is silicon nitride. So as part of the platform, we can integrate silicon nitride wave layer on top of silicon, and we can make waveguides in silicon nitrides. And we have some advantages to use silicon nitrides in combination with silicon. So the refractive index is lower, and very important too, the thermoptic coefficient is also lower. So for the thermoptic coefficient, we can use it to build devices which are less sensitive to temperature. And for example, the multiplexer, which is useful in transceiver circuits, I have the schematic here of the transmitter circuits for data communication applications. It's important to have this multiplexer which is not very sensitive to temperature, because in the data center you have a very different temperature change between the transmitter circuit and the receiver circuit. So we've demonstrated multiplexers with low thermal sensitivity. Silicon nitride is also interesting for a coupling scheme, so to couple the light from the chip to the optical fiber. And we've demonstrated broadband grating couplers in silicon nitride and broadband edge coupler in silicon nitride too. Okay, so now I will say a few words about active devices, which are very important for the TACOM application too. So first, the PN junction modulator, which is based on Mach-Zehnder interferometer. So we have a PN junction in the middle of the waveguide, and by applying a bias, we can tune the interferences of the interferometer at very high frequency. We can go up to 25 gigahertz in terms of bandwidth, and in terms of data rates, we've demonstrated 64 gigabits per second NRZ and 32 gigabo AM4. So it's very interesting for high-speed interconnects. So associated with the modulator, we have the photodiodes that we need to be as fast as the modulator. And the geometry we use is silicon germanium silicon with a germanium sandwiched inside the silicon. And we've demonstrated high frequency too with 35 gigahertz bandwidth and 64 gigabits per second NRZ transmission. Okay, and the last important building block is about 3.5. So we integrate 3.5 material epitaxis on silicon in order to make hybrid lasers. So how does hybrid laser works? So you have a schematic of a DFB laser on the top right of the slide. So the gain medium is in the 3.5, and the grating of the laser is in the silicon. So the cavity is in between the 3.5 and the silicon. So doing that is very interesting in terms of packaging complexity. It reduces the packaging complexity, so it's why it's very interesting. So the work we have done as part of the IRT Nanoelec program is to develop a process of the 3.5 in a 200 millimeter in the 200 millimeter fab of CLT. So we start by bonding a die of 3.5 epitaxis. You see here a picture of die bonding of 3.5 on silicon, and then we process it in 200 millimeter. You see here a SEM picture of pattern 3.5 waveguides with silicon waveguide underneath, and then we finish with the backend associated with the 3.5. And doing that, we've demonstrated a functional laser. So, for example, here you have a spectrum of a DFB laser. Okay, and I'm finishing with 400 millimeter platform. So what I've presented now in terms of results, it has been obtained in the 200 millimeter platform of CLT, but we are moving now to 300 millimeter. So everything that I've shown, we're transferring it to 300 millimeter, and we have already some very interesting results. So why 300 millimeter? It's because it's everything is better actually in 300 millimeter in terms of process uniformity and control, thicknesses of material, etching control and planarization also. And very importantly, we have access to immersion lithography with a very high resolution, and we have first results with a minimum feature dimension of 60 nanometer for trenches or lines. And we also use optical proximity correction to be able to have these very small features at the same time for the lines and the trenches. So a few examples of very good results that we had in 300 millimeter. So for example, for the grating couplers, we can have these very fine features, and we can improve the insertion loss from around 2 dB per coupler to 1.5 dB per coupler. And we're still working on this optimization to improve again losses, insertion losses of this very important device. So it's an ongoing work, but we're going fast, and we plan to propose a full platform very soon in 300 millimeter. So this is a summary of what I presented. So the main fact has a very low propagation losses in silicon and in silicon nitride waveguides for classical applications and for quantum applications. The full component library that we have, and maybe I forgot to say that we propose the access to this platform as part of multi-project wafers. The building blocks with silicon nitride in top of silicon for 3D photonics, the lasers with using 3.5, and the work on LiDARs. So I want to thank my colleagues. So all the lab have participated to these results, and also the PhD students, and of course the clean room staff. And I thank you for your attention, and I'm ready to answer some questions that you have.
Thank you very much, Quentin. No questions?
Do we have questions?
I don't think so.
Okay. Thank you.
Okay, so we now are moving to the next presentation from Prometheus. Prometheus is a researcher at the ITM Research Institute in the Polytechnic University of Valencia in Spain, and he will speak about a project on enabling the development of field programmable photonic gated arrays. So we should be able to give you the floor, Prometheus.
All right. Perfect. Am I audible? Hello?
Yes.
Yeah. Can you please confirm that I'm audible? Right. Start off. So depending on where you are in the world, a very good morning or a good afternoon to you. My name is Prometheus. I'm from the University of Polytechnic de Valencia, and I'm also founder of Hyperonics programmable photonics. And here I'm going to talk about field programmable gate arrays on a generic level about programmable. So to start off with, motivate the need for programmable photonics that we have done ourselves and the work that we are planning, and conclude. Right. So we started working with programmable photonics somewhere around 2015 with this whole idea of the field programmable photonic gated array, which is and one thing we found quite interesting when we started off was that there were several concepts which were already using the idea of a generic platform to suffice multiple needs. So one of them, for example, if you're X program, they have done an analysis whereby if you make a which is reusable, so a reusable rocket in that sense, then you actually gain a lot for the economy of scales that come across. And this, in life in general, we have seen it in electronics with move from ASICs to FPGAs, in networks where you have software-defined networks, and in radios as well where you have defined So what do we really need from moving to programming circuits? In photonics, be it by design or how the progress, we have already seen that we mirror a lot the developments in electronics. So what we always like to do is start off with what electronics has seen, take it as a motivation, learn the lessons from there, and move forward and try to do the concepts in photonics thereafter. So FPGAs are right now a very common and popular concept in electronics, and moving from ASICs to FPGAs, what we see that it occupies around 50% of the market. The way this trend developed in electronics overall is whereby in 1940s, 1950s, you had these discrete devices coming up, which we have seen in photonics as well. Then you moved on to more ICs, more complex circuitries, then application-specific ICs and microprocessors, whereby around 1980s we came up with, we realized the concept of FPGAs, and now you have this sharing of the market between FPGAs and ASICs. And the main reason for this can be divided into two things. It comes down to cost, but cost in two different levels. So one is the time in itself, because I'll just try to get the pointer up. Yeah. So which is the time to market. Time for companies also translates into cost in some other ways. So that's something which is very useful. So having a generic platform which you can replicate in multiple units and provide to multiple users always helps out, because then the time to market is very low. And you share the non-recurring expenses. So that also implies that especially for medium scale implementations, you distribute this non-recurring expenses in multiple users, whereby your costs come down quite a bit. There are other advantages as well, but these two are the primary drivers and the primary motivations for moving to programmable circuits or the idea of programmability in general. What we propose over here, and our whole idea of moving to programmable photonics, does not only encapsulate working on photonics, but also integrating electronics in there. So it's basically a harmony between electronics and photonics, whereby you utilize the best of both worlds and try to provide better functionalities and improvements in the technology in itself. In regards to the fabrication and the non-recurring expenses that I was talking about, and the timeline associated as well, I guess most of you are familiar with the fabrication flow, whereby you start with an idea, you have the fabrication, etc., coming off. And our goal in this case is to have it distributed across multiple users with the use of a generic hardware platform, whereby we bring down both the cost and the timeline associated with it. So you start off with the fabrication of this generic platform, leading on to encapsulation and the assembly, which would start off with the packaging of the chip, and then encapsulation of the assembly with any drivers, etc., that is required, leading on to a section which is a closed encapsulated subsystem, which you can see in this figure over here. You, of course, in every stage have to do the verification as well, whereby you have the complete hardware, which you, after further verification, can send to the end users. And another thing which is important in this case, of course, other than the hardware in itself, is the programmability which is provided by the software. So this added value through the software is something which we are concentrating on a lot as well, because it's a combination of both the hardware that we provide and the software solution, which is, in fact, the enabler to use the hardware. Right. So moving towards the FPGA idea, as I had mentioned before, we started working on this around 2015. So in photonics in general, the way the trends moved, we had reconfigurable aspects coming across in various formats. So you had circuitries, relatively simplistic ones starting off with, and then you added multifunctionality to this, or a few functionality at first. We moved on to multiple interferometers and circuits, and then around 2015, we started working on this hexagonal mesh idea, which is the basis and the core of the product that we do have, or that we are developing. And then we decided on adding a few things as well, whereby you have things like high-performance building blocks to support the core, and you have your inputs and outputs that are required as well. I'll come back to the core in itself and the high-performance building blocks in one of the later slides. So again, drawing a parallel from electronics, what you generally see over here is that if you shift the progress of electronics by around 30 years or so, which marks around 1960s, the advent of photonics in general, or integrated photonics, this is where we started off with standalone devices, with discrete devices, etc., moving on to more simplistic structures, more complex architectures and circuits, into the aspect eras, which still is very common in photonics. And then around the 2015 mark, we came up with the FPGA idea, and that's what we're trying to commercialize and make into a complete viable product. Now, the basic ideas and the concepts behind it. As I had alluded to before, there are multiple sides of this. So one, we divide this into different tiers. So one, which you see over here, this is the photonics in itself, the photonic chip, which consists of the core, which is the hexagonal mesh. We have high performance building blocks. Again, this is a similar concept to what you have seen in electronics, that you can have a product with a very specific programmable core, but for certain end users with certain requirements, you can add high performance building blocks, which can be modulators, which can be high Q filters, etc., along with the core to facilitate functionality in order to ensure that you do not lose any functionality because of the programmability aspect. So this forms then the entire photonic circuitry, which then would be packaged and would fit onto a platform like this. The rest of the platform, other than the photonics part, is the electronics, which includes the drivers, the readout system, any sort of processing that you want to do here. So to form anything required and dealing with controlling the circuit and to form a full closed feedback loop, which is the electronics tile. And to govern all of this, to drive all of this, we have the software tier. This software tier, we want to make it as flexible as possible. So for example, someone coming from networks can use it directly, the hardware, as a black box and program or basically achieve a certain functionality as they desire. If the end user wants to do their own configurations, they can as well, although we do provide our self-configuration algorithms, and this is all driven by a backend API. In the end, then, going into details of every tier that we have, what we propose is a solution which would look like this, where you can again see the hexagonal mesh, which is the core coming across. These smaller blocks on the side are the high-performance building blocks. And you have the fiber array as well, connecting onto the photonic integrated circuit, providing the optical IOs. You have drivers across and readout systems as well. So this, for example, can be a laser, which then comes back into the photonic chip if you want to keep it outside of the chip. But as we have seen from the previous speaker, there are possibilities of incorporating the laser in the system as well, in the photonic part of the system. And then you would drive all of this and control and manage the whole system using a software system, which looks like this. So this would be a GUI, whereby, again, similar to what I mentioned before, we want to afford as much as flexibility as possible. What I mean by that is an end user can use a GUI like this, just select the channels that they want and route the signal. But for some reason, if the end user has certain algorithms in mind, which they want to do, which they want to implement, we afford the possibility of doing your own coding and configuring the system as per your desires, your algorithms, etc. as well. So we want to cater to as many users as possible in that sense. Right. So a bit more detail about the electronic systems in itself, because this is something which at the moment we are moving from discrete units to making our own designs to make it very compact. The part we start off with is the driving array. This, as you know, is to drive any sort of phase shifter, so the gated mechanism within the photonic chip. And then the output from the chip is fed into a monitor system, which is then fed into a processing unit to complete the entire feedback loop. The processing unit is where we have our backends running as well. So at the moment, we were using a PC for this, and then we are moving into using a processor to have this as close to the chip as possible, and then make it into a small, compact subsystem, which helps out a lot, especially if you're planning on using this in a larger system in itself. Again, coming back to the software once more. So one of the features which we are adding in here is the lower level layer, which I mentioned before. This has basic routines, etc., which will be hidden for the end user. So this is basically the backend, but this also enables a custom coding platform for every end user as per desire. This adds a degree of freedom, which is not compulsory, but is an option for the end user depending on their requirements. The high-level system is something which I would assume most users would be interested in. This in itself has pre-characterization of the FPGA. It has added functionality such as configurations, auto-routing, and user-defined configurations as well. So one of the possibilities, which I have a slide on later on, is also uploading your own custom mask and asking the system in itself to basically fabricate or actually design a path which then can replicate that custom mask that you require. So custom transfer function in that case. And we also provide within this configuration part a monitoring system whereby you can assure that even within certain limits of temperature drifts or within certain limits of temperature drifts in the photonic integrated circuit, you still maintain the performance as per desire. So moving on to some of the results and measurements that we have done, what we have already demonstrated is for the control of the circuit, we are using some advanced machine learning algorithms. I won't go into the specific details of them, but if you have any questions, please feel free to ask. What then happens in the back end and what we have demonstrated to date is, for example, a beam splitter. The one example you have over here, this was for a 1/8 beam splitter, whereby you started off at the initial condition of the chip. What I mean by the initial condition is that you have phase errors coming off across because of the fabrication variances of each part of the circuit in itself. And then we have this automated mechanism to configure the chip so that you end up with a 1/8 beam splitter. As you can see over here, we have used several cost functions to optimize this as well. Excuse me. And then based on the cost function that you use, you require a set number of iterations to configure the chip, whereby after, in this case, it's 20 iterations, you will see that your performance is what you desire it to be. We have done this for ring resonators for different filters like Mach-Zehnder-based ones as well. And what we have done as well is a comparison of the dynamic performance of such configurations. What I mean by that is switching from one form of a filter across one particular path to another filter across a different path. Sorry. And we have compared these results with the static performance. This was also done to ensure that we do not lose anything when you reconfigure. So move from a static environment to a dynamic environment. Unfortunately, I cannot present a video over here, so I won't go into the details of that, but please feel free to ask about that if you're interested. Another feature which we personally are very proud of, which to me is very, very interesting, is that you can upload your own mask. This is what we call as the mask. So basically, if you need a certain filter with set parameters, you know how the filter should look like. You can basically just upload this into the system, into the program in itself, and then you will see that your control system based on the operations of the processing unit will configure and give you the desired filter performance that you need. So this is a very interesting feature. It gives an added degree of flexibility to the whole concept as well, which we are developing further and trying to integrate it into the entire system. In regards to the progress that we have made till now, as I mentioned, the concept, we have started working on it around 2015 with publications coming across around 2016-17 landmark. From the university end, we are working on an ERC grant. We did the FPGA concept and patents on that. We have moved on to improving the performance, improving the software and the and the control layer associated with this as well. A lot of the work also is on machine learning algorithms for self-configuration. And at the moment, we have new projects coming off, as you can see over here. There are a list of a few of them that we are working on, and we are trying to come up with the first prototype, which would be somewhere next year. So to conclude the whole talk, in regards to FPGAs or programmable circuits on a whole, there is a lot of scope. There's a lot of interest in this because it fills a gap which aspects themselves cannot provide for. There is improvements that still need to be done. So we are trying to tackle it in different fronts through different projects, different ideas, be that in the control lab, be that in the software department, be that in the physical design of the chips as well. And as I mentioned before, we expect to have a product on this, or at least the first prototype, beta prototype of this somewhere around next year. So hopefully we can get some, we already have some interest on this for testers, for people who want to give this a try. And we already are hosting some custom workshops to promote this further, to make available to the end user the ways of managing the software and how to drive it, etc., so that they're familiar with the software and the interfaces, etc. And my colleagues have also recently had a book coming out on this, so please feel free to read about it. This is a very complete book in the sense that it covers from the fabrication, from the big design side to the system level side of the whole programmable photonics concept. So yeah, if you're interested in this, please feel free to have a look. Thank you for your time, and if you have any questions.
Thank you very much, Prometheus. We don't have any questions on the chat. Maybe one. So we can see that it's probably still a research tool and thrust that you're working on. Do you see emerging applications for it in terms of what kind of, if you look at the photonics community, do you see people that specify some potential applications when things will be mature enough in terms of?
Yes, that's a good question. So to start off with this, sorry, maybe you can mute your microphone once more. I'm getting a lot of feedback. Yeah, thank you. So firstly, I do want to stress on one thing that from our side, we want to be application agnostic in the sense we want to make it as generic as possible. But the most interest we have, based on the feedback we have had from people we have been interacting with, have been, for example, from people working in data centers, from people working on beamformers, on RF filtering. We have people working on neuromorphic computing, for example, showing a lot of interest, quantum computing as well. So these are fields we are looking into. What we also try to do from our side is interact with them and try to incorporate some, especially in the software side, some custom requirements that a particular field might have, which is a very nice thing to do, because if you have a generic hardware which you can customize from the software end, that adds a lot of value to the whole product as well.
Okay, thank you very much. We can close the session, and thank you for your flexibility in the time. Thank you, Prometheus.
You're welcome. Thank you so much.
So we are now moving to the next and last session. Yet once again, sorry for the delay. You are still connected to the IRT Nanoelec workshop on bridging the gap between technologies and architecture. And the next session deals with cybersecurity. The first presentation will be given by Jacques Fournier, who is the head of a research lab at Leti in the system division, working on cybersecurity at the components to embedded system level.
Thank you, Ig. Good morning, good afternoon, everybody online. I have the pleasure and honor of introducing this session on cybersecurity. I will try to keep it short just to catch up on some time, and I also unfortunately have some operational constraints due to the whole havoc with the coronavirus and things to be reorganized at the team level. So the objective of this presentation is to give you an overall idea of the whole complex issues linked to the cybersecurity of industrial IoT, and hopefully settle the ground for the other two presentations from Schneider Electric and STMicroelectronics. So when we're talking about industrial IoT and cybersecurity, I'm just trying to make the... Ah, pardon. Okay, thank you. So the complexity with this whole story is that we have smart industries, and with the industrial control systems and all the legacy systems, on which there is a clear advantage of adding IoT applications and devices to enhance productivity, to enhance maintenance, and monitoring, and etc. But one of the main problems that we have to deal with is that we have this entire industrial control system legacy, on which we are adding IT devices. And in terms of functionality, integration, and final objectives, there are many, usually many things which are we don't work in the same direction. And there is also a lack of understanding between those two worlds, which have been evolving and moving forward on two separate tracks, and on which we are now asking them to reunite and work together. And of course, there are many buzzwords, there are many issues to cover. The issue of cybersecurity, one of the main challenges linked to the smart manufacturing, smart industry, industrial IoT, industry 4.0, whichever word you want to use. And cyber attacks on such infrastructures today is not only a social and media phenomenon, but is also a big business in terms of revenues which hackers are trying to derive from this. There are also major security issues from national point of view. There are many business issues. There are companies which are victim of cyber attacks and which end up filing for bankruptcy due to that. We have seen stories last week. So there are all those commercial, social, and technical aspects linked to cyber attacks, especially on industrial systems. And one example of kind of devices and platforms which have been enhancing the whole phenomenon, and is, for example, most of you must probably know the Shodan website, on which you can have an overview of all the devices which can be which are connected or which can be accessed through the internet. And derived from this Shodan, you have the Shine, the project Shine, which is a project which demonstrates how by just having this mapping provided by Shodan, you can derive information from industrial systems. And another declination of this is the Red Tracks projects, where actually attacks have been demonstrated on such infrastructures. So this is one of the typical, let's say, examples that can be cited of open doors on the cybersecurity of industrial systems. So why is it so complicated when it comes to securing IoT infrastructures for industrial systems? One first issue, which I already mentioned, is this the complexity due to the fact that we have two worlds which are converging, trying to converge towards one same goal, toward the IT world, the OT world, and you have to have these those experts from the two fields who would work together, at least start to understand each other's language, start to understand each other's objectives, and try to work together, which is something which hasn't been solved yet, as far as I know. The other main challenge and problem with such applications from a cybersecurity point of view is that in terms of supply chain, in terms of stakeholders, in terms of device providers, solution providers, it's a whole world out there, and we have to try to have a scheme which takes into consideration the fact that we have several sources of equipment, devices, and solutions providers. We have this issue where we have this one conflicting issue of IT versus OT approaches is that until now, from an IT point of view, when you had a security issue, one typical way of dealing with the security issue is to shut down the system, try to see what's happening, sanitize the system, and then reboot it again. In many OT infrastructures, or in many industrial systems, or many critical infrastructures, we can't afford this. We have to maintain some the ability of service. There's a resilience issues, and for this, the security, the cybersecurity which is deployed on such infrastructures, has to be rethought and reworked again. And of course, in terms when we're talking about industrial IoT, we're talking about business, we're talking about how do we evaluate and try to have a return and evaluate the return on this investment, which we can get from implementing a particular security mechanism, because usually implementing security mechanisms has a cost, does take time, and we have to justify for this additional cost. And there is a whole discussions, issues, and research projects and how to calculate a return on the investments for security. And another aspect which is emerging right now is how do we set up and develop policies from an industrial point of view when there are cyber attacks. Just like there are the development of policies when we have cyber attacks from a national point of view. Today, for example, we have different countries who have engaged into cyber retaliation, or who are talking about cyber wars, because there are policies which have been developed around that. From an industrial point of view, there is also a whole field which is emerging today as to how to, from an industrial point of view, manufacturing point of view, how do we handle data information about emerging cyber attacks? How do we handle when we are victim of a cyber attack? And when do we decide to stop a manufacturing plant and secure it against a potential cyber attack, versus the cost which it might incur to take such decisions? So when we take a very global and high-level representation of an industrial control system with three main levels of a physical level, of a control command level, and supervision level, there are many entry points in terms of cyber attacks. There have already been many studies about how to detect, monitor, and secure infrastructures from a network point of view. But what we are seeing more and more today is the active role which the device itself can have in terms of level of cybersecurity of the entire system, and in terms of how the device's vulnerability can itself be a major cybersecurity issue. So the device, the embedded system, is what we are currently working on in Nanoelec. That is in the sense that those devices are not only the objects which will be hosting, running, and delivering part of the cybersecurity solution for industrial control systems, but could also be entry points to carry out attacks. So when we take this the cybersecurity link to an object which is integrated into an industrial IoT system, there are four main aspects which need to be covered, and which I will introduce very rapidly here, and some of which will be discussed into more details by the following presentations. The first aspect which needs to be taken into consideration is the design phase of a device. So the key word which is mainly which we hear most of the time those days is the secure by design. That is, we must integrate the security aspects right from the design at the design time of the device. It's easy to be said. It's another issue when we try to implement and deploy it. The first thing is there are two main approaches. The first approach is to say, hey, let's see what there is today on the shelves, and how we deploy the best secure solutions based on what's already on the shelf. And the second approach, which is more long-term vision, is how do we redesign things to be so as to be secure right from scratch. For the first approach, the difficulty is that you mustn't be phobic to all the key buzzwords of trust something. Trusted platform module, trusted execution environment, trust zone, trust this, trust that. And there are loads of keywords which have a significant technical meaning. But you have to get into it. There's a whole process of learning what's behind, and understanding what's behind, understanding what you can do in terms of security with all those concepts and objects, and what you cannot do, what are their limits, and how to best take benefits of them. And of course, this is one of the aspects which we work on in Nanoelec, which is to say how we can build systems, secure systems by design, based on those off-the-shelf technologies. And we have with our industrial partners of Nanoelec reference designs to demonstrate this. And in the long-term vision of things, there's the whole notion of, once we have those concepts, those reference concepts of how to deploy security by design on those platforms, how do we generalize those concepts on other platforms, on future platforms, and how do we define and specify future platforms so as to be able to better integrate those security concepts. The second aspect is to say that once you've designed things, you've got to find a way to have confidence into what you have in your hands and what you're deploying. And this confidence, you can either trust your device, the device manufacturer or provider, or say, hey, I better have try to see with a third party, and who would do tests to verify the conformity of what there is in that product versus what it's supposed to do in terms of security. So this is what I mean by certification. And it relates to the whole aspect of how do I verify the security features which are supposed to be in my product, and make sure that the way I'm deploying it in the system is is relevant, corresponds to what is recommended by the device provider and by the corresponding certification label. So in terms of certification, there are lots of discussions actually at the national, international levels. A couple of keywords and entry points which I can provide is at the French level. The French ANSI has been setting up and promoting what we call the certification de premier niveau (CSPN), and which provides a certification scheme environment which can be deployed for IoT for IoT devices for industrial systems. There are also other schemes like the IEC 62443, which is an international standard for security conformance for such devices. But the latest evolution in this field was the adoption in May 2019 of the EU Cybersecurity Act, which defines a scope for the certification of IoT devices in general, with a definition of 3 levels: basic, substantial, and high level. In a nutshell, basic is self-declaration of what you have implemented, with eventually conformance and testing reports provided to the certification body. Substantial, you provide your device to a testing laboratory, third-party testing laboratory, who will run the test and validate the conformance of what you have said with respect to your specifications. And high is, for those who know, who are from the field, is equivalent to what is done today by ITSF laboratories for common criteria certifications. The third aspect is, once I have designed the thing, I have certified it so I can deploy it. And the whole deployment of the devices is an entire aspect in itself when you have to consider cybersecurity. It not only involves how you install your device, but once you install it, how do you initialize the crypto keys or the sensitive data, which will allow your device to communicate and interact securely with the rest of the system. How do you authenticate your device? How do you maintain your device in terms of, especially if for industrial systems, usually you would deploy devices for a long period of time, where you won't be changing your objects or devices every 2 years. We're more on towards decade level in terms of time frame. So you have to put into place maintenance update mechanisms. And today there is no specific standard with respect to that. There are discussions and proposals which are being put forward, but given the heterogeneity of the devices involved, their nature, the complex and very diverse supply chains, having a global and structured approach in terms of maintenance deployment is very complex today. There are specific solutions which are deployed per product, per device, per manufacturer, but it's still something which it is still a major challenge, I would say, when talking about cybersecurity of industrial systems. And the fourth aspect is, once you deploy it, how do you manage it? And how do you manage it in the long term? I already mentioned the fact of the idea of having mechanisms to update it in real during the lifetime of the product. But there are also emerging concerns about how do you make sure your device is secure, your device and solution run by your device is secure on the long term. I want one funny thing which some people say is it has to be future-proof, future-proof towards tomorrow's attacks, again, tomorrow's cybersecurity issues. One thing which is clearly emerging today is the threat which might pose the emergence of quantum computers against current cryptographic algorithms. So there's this whole discussion about how do we standardize about the standardization of post-quantum quantum resistant schemes in terms for cryptography. I mentioned about secure updates. There is growing concern, issues, and studies from an academic and research point of view on the convergence between safety and security, which I already mentioned, and in terms of resilience. And to do this, you have to work on the theoretical and research side of things, but you've got also to have a proper testing environment to run the test and make sure that the solutions and devices you're deploying can actually work in real life scenarios. So in a nutshell, those are the main, in my opinion, four main issues which need to be addressed from a cybersecurity point of view. And Nanoelec has been so far, with the help of all the academic and industrial partners in Nanoelec, very active in all four fields. From a design point of view, as I mentioned, working on the implementation of reference designs for devices, secure devices for such systems. In terms of certification, here at Leti specifically, there is an accredited ITSEF evaluation center for testing high levels of security. And based on the expertise of this team, the whole Nanoelec benefits from their expertise to address the issues linked to certification. We are currently working with industrial partners in trying to test and develop user-friendly security and deployment schemes for their products. And in terms of management, in a more long-term vision, we are working on things like new cryptographic schemes resistant to quantum computers, and more today. And this will be one of the major focuses for the future roadmap. Is to have securely implement and embed artificial intelligence into those devices. And of course, all this is possible thanks to the whole testing and demonstration infrastructure, which is available here at Nanoelec for specifically for industrial systems, but more also in general for testing integrated circuits and communicating devices. Thank you for your attention.
Thank you very much, Jacques. Were there any questions during the chat? On the chat?
No question.
Okay. Maybe because the time is flying, I suggest that we move to the next presentation. So it will be given by Jean-Michel Brun from Schneider Electric, where Jean-Michel is the Chief Security Architect of the IoT and Digital division. He has been working with Schneider, occupying different roles in R&D and security for more than 20 years now. He graduated from CPA Lyon, from a master's degree with a major in software engineering. And he's going to address in his presentation the challenges of using public infrastructure, which are quite complex measures to secure communications and IT networks in the framework of industrial networks and systems. So I'll close my...
Hello, do you hear me and do you see me?
Yes, we hear you.
Okay, good. So, yes, thank you for the introduction. I think I have to respect the time, 15 minutes. We start on this. Okay, so I will go. I try to go in detail and to define the interest, the use of the PKI, the global. I would say these security tools, asymmetric encryption, certificate, public infrastructure for industrial environments. So as you know, this is technology, I would say, coming from IT, and we are effectively studying and using, or want to use to secure products or industrial products. So first, just to underline that this security tool, we say, can be used for several features. First is to get the integrity of what I put in bracket executable, so through the digital signature. To example, the firmware signing, software signing. I make the distinction because most of the software are running on Windows, so there is a specific technology, the Authenticode Microsoft technology here. We also can use this technology for device authenticity. Maybe the first thing we are thinking is to use it to secure the communication, the confidentiality, integrity, non-repudiation between entities. And in industrial system, we have put this example of entities S2S, software to machine, machine to machine, and behind this, the user to machine, and it's also used for the authentication of users through certificate in a dedicated operating mode, I would say, for the user. And in addition, we can also bring some authorization information, and for instance, by injecting information about the role, role-based access control role, for instance, inside the client entity certificate. So this is, I would say, link of this technology can help us to handle the industrial security standard requirements. I put here two main standards for our environment, the IEC 6443, and precisely the 4-2, which is, I would say, it's a high-level point of view, a long list of security requirements in the context of industrial automation control system, and also the IEC 62351, specifically the part 8 and 9, if you want to have the detail, describing security requirement for power system. Yes, it's quite slow. Okay. Yes. So related to specific technical feature with this infrastructure and this tool, I would say. So the interest of using a PKI and the associated certificate, etc., is first to bring trust to all the different certificates, entities. So when I speak about entities, we are, I think, specifically on the device, the user, the software, and so on. So here, the interest of course, of the PKI is to have a certificate authority. So for people who know this, it's maybe obvious, but it's very important. We At the opposite, we can remove the trust by making revocation. And for this, we have, for instance, the certification revocation list, the CRL. We can also have some information through CSP servers. We also can define a lifetime, a limit of time, and having reference by timestamping of the entities, which is important in terms of defining a limit of the trust or a limit of the use of or the access of the user or the device. Very interesting point is to have a centralized management of different entities, and it's for complex infrastructure or big infrastructure. It will ease the commissioning, the decommissioning, the device replacement. After we have to take into account a list of elements. I will detail further. And the PKI, we can have several trust models in the PKI, but specifically, it's not the unique approach, of course. The hierarchical trust model, where you have the drawing here, fits an industrial system structure where you have, when you are defining your industrial process, you have, of course, to design your automation system, and it's well defined, formalized element. So the associated trust model with a hierarchical point of view fits this. And in addition, of course, very important, a process, an industrial process, stay for a long time, and in the same time, there is a regular evolution because to produce new things or to take evolution, an industrial system is evolving regularly. Not every day, of course, but during the long lifetime of this system, we have to manage the possibility, or it's mandatory to have the possibility to make evolvement. And with this trust model, you can also manage this evolution. After, of course, you have to take care regarding your design. So associated to that, I will just to underline a list of challenge. So maybe are of course obvious or for people evolving in this area. So this is also to underline for me the difficulty of the convergence between OT and IT, and when I say security coming from IT. So I will the list, and this is at the challenge are at the different level. So first, behind the use of certificate and PKI, the baseline is to have private and public key. So we have, of course, to store securely this information. To secure in confidential way the private, and in an integrity way the public key. So for that, you need to have complementary elements. So I would say at the PKI level, generally we are using a hardware security module to manage certificate authority. At the device level, it's the concern in the IoT environment, we can use secure element or TPM, maybe more secure element. TPM is more for the PC environment, and but no specific original information using smart card or key, secure key for the user. So first, this is the baseline, and of course, there is an immediate impact in the hardware of our product. And the second element is to manage and to create a PKI, certificate authority. It's very secure process. Security you have when you are doing the creation of the TA, the certificate. You have to generate regularly the CRL if you have chosen this technology. it must be done seriously, securely. And it requires strong competency, where we have here a kind of scarcity of this competency. In the specific, in the context of IoT, we need several PKI, and it's associated to what I call the operational responsibility. So if I take first example, at our level, at the manufacturing level, for instance, we are signing the firmware, and then we need a PKI to manage this firmware signing, and this is our PKI under our responsibility because we operate it, and this is linked to our environment. Then we are selling our product to a system integrator which will take the product and make the design of the end user process and will configure, install on the customer site. So I say potentially during this phase, he has to make tests, he has to make the verification and to establish, for instance, the secure communication. He will need his own PKI to make the test. And then after, when he will transfer the installation, he will the end user will need his own PKI with corresponding to the final commissioning, running the system in the end user infrastructure. And because this is the end user who will operate his process, it's under the responsibility. So you have to manage, I would say, this complexity, and you have to understand all these elements. So if we go in more detail related to the PKI use, and coming back to the use, for instance, for secure communication, I have a system where I need my global infrastructure need to set secure communication between the device, between the software, between the user, and so on. So we have to solve first the notion of lifetime, or we have to take into account the lifetime of the system. And then by definition, there is an immediate consequence when you are generating a CA, a certificate authority, an entity certificate. You have to think about the lifetime of the certificate. You have to think about the revocation. You have to think about the renewal. And in addition, just to make the link with some current topic, we have also to think to the potential shift, or the shift to the post-quantum algorithm. So just a very simple question. What is it possible? What is the cost? How to manage that in an operational system where the end user is producing every day, every minute? To also take into account of the constraint of the PKI, we have, of course, to think about the installation and the replacement, so to manage in a secure way. And the secure communication is a key point. And we have to think. We have to allow with this element, this tool, I would say PKI tool. We have to allow an offline device enrollment. So this is maybe we can debate the bad approach, but you can do that manually. So you have to generate the key inside the device. You have to generate or to get the CSR, the certificate signing request, generated in the device. You have to bring this to the CA. You have to ask for the generation of the device certificate and to bring back to the device. And this is a manual operation done by the user, the system integrator, the end user. And then, of course, all this operation must be secure. So you must authenticate. You must bring the right authorization to the user, to the automation engineer or the secure administrator. When the process is running, you have also to allow online device enrollment. Just take the example of replacing a failed device, and you have to ease at the maximum the enrollment. So here you can use, for instance, enrollment protocol. So I put here, there is several, for instance, two example of protocols, the SCAPE and EAST. And just for information, this list of protocol, enrollment protocol, is listed in the IEC 62351. And this is also maybe not only a challenge for the IIoT. For instance, SCAPE is not officially validated. It's, I would say, a de facto standard or de facto technology used by different products in IT world or in network world. But we know that there is some vulnerabilities. SCAPE can be used only with RSA and so on. So this is also the limitation of the technology we have to manage in the long lifetime of our product. And also we have to decide in terms of policy and to manage, technology speaking, the renewal of the certificate. And of course, to deploy, we need to deploy the different certificate, the certificate of new device, sorry, to the entire infrastructure. Of course, only to the device you want to communicate with. And to manage the global security and so on, we of course need the connection to the CA, the end user CA, and maybe with IoT there will be more and more internet connection, but at this time mainly it's specific for critical, it's on-premise installation, so you need a CA at the premise of the customer. And you need to set, for instance, connection for the CRL to detect if there is some revocation through a CRL distribution point or a OCSP responder and so on. So this is just to list some example of for me, the main challenge in the IoT environment. This list is not complete, so I try to give the main point. I try to respect the time, so please tell me if there is time to have a question answer. No?
Yeah, there is no question on chat, but maybe I have one that will make the link with the last talk. Can you comment on how you partition your security actions at the interface between software that obviously you are dealing with and hardware that you supply from partners, whether it is at the embedded systems or the components? We'll speak about ST microcontrollers afterwards. So is there some work that you do on that?
If I understand well your question, yes. So, for instance, software, we are speaking about SCADA connected to device, effectively. So this is why we are studying interest of PKI to, for instance, to manage secure communication. I would say I will call it a machine-to-machine secure communication, and it will rely effectively on the use of secure element where you are able to manage the private key and the certificate of the device, and also associated to the deployment of the associated certificate of the SCADA in order to establish secure communication. So this, I will say, this is my answer. Please confirm if I understand well your question.
Okay. Sorry. Yes. Okay. Thank you very much. So let's move on. And so thank you for delaying with your presentation and coping with our constraints. So the last presentation will be given by Nicolas Anquet, who is working with ST Microelectronics in the microcontroller group as a chief hardware engineer, and he will present how some of the solutions of the safe microcontroller family of components, STM32, can address some of the challenges of industrial systems on the side of security.
Hello, everybody. Can you see me and hear me?
Yes, very well. Thank you.
Very good. So thank you very much for your invitation today. So yes, I'm going to quite briefly explain what ST can propose to the securitization of the industrial IoT through its portfolio of secure and standard microcontrollers. And as you mentioned, I'm working in the microcontroller division in the architecture team, in charge of all the security aspects around STM32. So the goal of this presentation is to explain how ST Microelectronics' portfolio of standard and secure microcontroller components can serve the industrial IoT, as very well explained by previous speakers. This topic is quite complex, and the ecosystem is complex, and the technology involved are coming from the IT, but yeah, we are dealing with some complicated technology and very individuals that are very eager to break the security for their own good, I would say. So this slide is just to mention that ST has been in the security market for more than 20 years now. So we started with smart card in the smart card ecosystem, providing solutions for telecom through SIM cards, for example. We have been working also to embed specific application in SIM card. But then growing from SIM card to application processor, for example, I was working for security in ST Ericsson family of application processors. And we have been deploying, for example, on those application processors for mobile phones running Android, some trusted application running on a global platform compliant trusted execution environment. So that was the starting of a complex offering with a hybrid of software and hardware running on a ARM Trust Zone CPU. And from the secure micro side, they have been working, on top of smart card business, they have been developing contactless cards on NFC solution. And also my colleague in the standard microcontroller division have created the world first Cortex-M, ARM Cortex-M microcontroller in 2007, starting the very successful STM32 family. So today we are in 2020. Clearly, the security market is now booming with a multiple of ecosystem. Let's say I'm listing IoT, industrial, and smart driving, but I'm probably missing few of ecosystem. ST offering for this ecosystem is still STM32, which is very strong, very versatile and easy to use. But at the beginning, we didn't start very secure. We were mostly relying on ST secure micro solution like eSIM and STSafe to boost the security of the overall product. But in the last years, we have been working in STM32 team to increase our level of security to offer more alternative to our customers in deploying security for IoT and, for example, for IoT and industrial. And today I'm going to talk specifically to. I'm going to give a small focus on industrial, on IoT. So we are providing solutions, but how our customer choose what solution to take from ST, because we have hardware, but we have also in STM32 we have partners, we have embedded firmwares, we have that can be used. So it can be quite daunting to find the right trade-off when designing a product. So I'm going to quickly explain how it's usually done in the industry to design a secure product. So first you start with the risk management. So first you have to understand the value of the assets you are going to protect. For example, talking with all the stakeholders that are going to use the assets. You are as the owner of the product, you estimate the value of the assets. Then you understand the threats and vulnerabilities associated with these assets. So this is Mr. Threat here. That's going to exploit possible attacks on, for example, if your product is connected to the internet, the possibility of attacks are quite daunting and numerous. And for each of those attacks, for maybe internal risks that are unknown from the outside world, you have to you have to develop security strategies to reduce the risk using the right level of security in line with the value of the assets you want to protect. Because as it has been mentioned before, sometimes you have to find a good trade-off between security and the cost of securing the asset. Otherwise, the cost of your overall product would be not competitive. And the key recipe for success in this endeavor is usage of cryptographic tools on, for example, integrity methods. But those tools, those cryptographic tools and methods, will be part of a design strategy. It's not enough to have an AES-256 to secure your product. You need to think it from the ground up. You have to think of as the expert used to say, the devil are in the details. So having a great AES engine is not enough to have a complete secure system. So the correct strategy to design a good product, the security of a product, is to start from day one, taking security into account. On how you do that, so you identify the asset you plan to protect, then you design the product based on the appropriate level of security for each of the assets you have identified. Then you are going to develop methods and process to protect those assets over the entire life cycle of the product. So that's quite important, because first you have to produce the product with usually quite sensitive firmware. You don't want this firmware to be hijacked during the production of your device. But then afterwards, as soon as you find vulnerabilities, you would want to upgrade the firmware that has been flashed into your device, your product. And sometimes some customers are really sensitive in managing the end of life of the product they have put on the market. So that would be the design strategy you have to follow in order to have a secure product. So in the context of industrial systems, I took the example of that has been mentioned before during the talks before. I took the example of IEC 62443. So the first step, as I mentioned, you need to assess the risk. So in the process suggested by this norm, you have a list of security requirements, and based on your product, on your system, you have to give a priority based on a security level you want to achieve. On this security level, so ranging from 1 quite low to 4 very, very high level of security, you would select the right level based on the probability of the attack from high to very low, on the impact of the attack from minor impact to very severe impact to your system or your component. So once you have defined the target security level, you will build your system from the component to the system level using the right security level, so from medium to very high. And then you will evaluate what you achieved deploying your system design with something called security level achieved. And if your SLA match your SLT, then you have achieved your target. If you are below your target, then you have to take the decision. Do you need to come back to the design board, the drawing boards, or can you live with the discrepancy between the target and the achieved level of security? So in order to help our customer to run such process, ST has a scalable security offer for the industrial IoT, because this process is typically recommended for the industrial systems. I will not spend too much time here, just to mention that so in the microcontroller memory and secure MCU division, we have a wide range of portfolio of products that can be used to secure such complex ecosystems, so computer, robots, cars or trucks or delivery system connected to the internet or talking to each other. So first thing we could do, for example, with an ST safe, we could have a secure ID authentication mechanism to verify who is talking to whom in a secure way. There would be some solution to implement secure storage of keys and parameter, either in ST safe or in STM32 with a good level of security, but I will come back to this. Then at lower level, at datacom level, we have solution to secure communication, to secure over-the-air firmware install and updates. For example, using eSIM and also ST safe on STM32. On the root, the core of the security for those two datacom level and application level securization system is the hardware level root of trust, the secure boot, sometimes the device integrity to check that everything is running as expected on the component itself. So, and we have two main offerings in ST. We have the ST safe offering and the STM32 offering, with obviously not the same level of achievable security that I'm going to explain now. So for STM32, we are targeting a wide range of applications from smartwatch to robots on washing machine or drones. So we have various level of security expected. So in order to help our customer to understand what they have to deploy on at which level of security, on using which component, which could be pure hardware, a mix of hardware and software, or pure software. We have analyzed the latest security recommendation from, for example, CZIP for global platform. And we have categorized 12 security functions that the customer should look at in order to secure their product. So, for example, we find a secure boot that I mentioned before. We have secure manufacturing, ensuring that you are provisioning the correct firmware in the microcontroller. I mentioned the secure install and update of firmware over the air. The usage of cryptography for authentication and integrity verification, etc. The management of life cycle, secure storage of keys, management of abnormal situation, like intrusion of attempt of physical attack on the product, etc., etc. On identification, authentication. So everything you have seen on the last slide is obviously present in the STM Trust approach that you can find right now on the st.com/STM32 Trust. So you have a bunch of, it's a kind of white paper with a link to key application notes on technical documentation to explain how to achieve this using either only STM32 microcontroller or a combination of STM32 microcontroller with an ST safe secure element. So I mentioned that so STM32 is trying to increase the level of security, so we cannot do it by ourselves. It will not be, nobody would trust only ST. We need to rely on a third party to attest that we have the right level of security. So we are using, so we have been embracing the ARM PSA certification program in order to assess our security implementation and to also to help the deployment, for example, of a trusted firmware application on our hardware. So the idea is we have an API compliancy, so you can take STM you can take ST trusted firmware to run your security on the microcontroller, or you can develop your own on top of ARM PSA APIs to lower the overall cost of the security on your microcontroller. Recently, ARM PSA has been, the certain aspect of ARM PSA has been taken at European level through CESIP. So CESIP is now level 3, I think is run by a global platform. And we are now working with labs in order to get a stamp that we are, for example, CESIP level 3 would be, we have some white box text testing of our security with a time limited. And then if the lab does not find any vulnerability, checking at our source code on a data sheet, on a detailed hardware specification, they would give us the CESIP level that we have been applied. We applied for. So today we have a CESIP level 3 for STM32L4 with SBSFU firmware. But we have also been approved compliant with ARM PSA level 2, which is also a white box certification by a lab, an independent lab, running ST trusted firmware. So STM32L5 is a Cortex-M4 with Trust Zone extension, and so the core of the security, trusted boot, firmware update, firmware install is running on Trust Zone, while the motor control or the non-security application is running on the non-secure part of Trust Zone. If you need more than CESIP, if you need common criteria level of security, for example, for your key storage, then we recommend that you use an ST-Safe product. And ST has a family of ST-Safe product called Secure Element. And depending on what you want to achieve for your security solution, so that range from IoT node to IoT infrastructure, you can choose either an optimized ST-Safe A, cost efficient, very good for authentication, securing connection, good for secure storage. It has been deployed to secure LoRa, Sigfox, and IoT nodes. So that's why they use probably an optimized solution because of the cost. Then when you need more flexibility, when you need to deploy your own Java-based security solution running on a super secure element, then you can use the ST-Safe J product that has been certified CC EAL5+. And here, obviously, you can do everything you need to have a good level of security for your IoT node or IoT infrastructure, even though I agree that even if you have a super duper ST-Safe J, and it's badly used by the overall product. The overall product, it's badly integrated. It has not been paired with some critical function running on the non-secure microcontroller, then you probably have an issue. So that's why it's important to. Actually, that's what we did in STM32 Trust. We do have also some. We propose some collaboration between STM32 and an ST-Safe. Probably, I think, through application notes or example of codes. And such solution has been selected by Nanoelec, where I'm talking today, in order to implement a securization of sorry, it was written. I wrote it on this slide. In the context of IRT Pulse, Nanoelec, securization of the industrial IoT. The CEA and our partner in the IRT has selected STM32 plus ST-Safe TPM in order to implement the highest level of security for their industrial IoT products. And the TPM is here. So this product is certified CC EAL4+, TCG because it's that's a consortium that is specifying the TPM. So that would be the specification for the TPM. Okay, and this is NIST FIPS 140-2. On TPM is very good for example, secure storage, managing a node in a network. Like Microsoft is very fond of TPM to secure a bunch of Windows computers connected to a network. And it's also able to run platform integrity at boot time on ensuring that any firmware upgrade has been verified is authentic. Wrapping up this talk, so based on your analysis of the risk, ST portfolio of standard and secure microcontroller is here to help you meet the security level target of your design. So you can, if you want to have something cost effective, for example, using STM32 with Trust Zone, you can go the STM32 route, implementing the right, following what we recommend in STM32 Trust. Or you can go the route of using a secure element like we did in Nanoelec with ST-Safe TPM, where the long-term keys, the very critical keys are stored in the secure element. And once when they are needed, the secure element will deliver session keys that are then used in real time by the STM32 microcontroller. Thank you for your attention, and I'm open to questions, if any.
Thank you very much. No questions on the chat. I think it was quite clear. I have no specific questions on my side. Thank you again for staying late to give your talk. So we are closing the webinar. Thank you to all the presentators and the attendees. We will post the videos of each sessions on our YouTube channel next week, early next week. We'll check with all the presenters if they are okay for sharing the slides, and then we'll share the slides within the community of IRT and set up something to share them with external people if they are interested. And to finish, I would mention that you can follow us on LinkedIn and Twitter at IRT Nanoelec. Thank you very much, and have a good afternoon and weekend. Goodbye.